The night sky pretends to be calm. We look up, and it feels eternal, fixed, peaceful, a silent dome of distant lights, patient and unchanging. But that is the greatest illusion the universe has ever sold us. Space is not still, it is not quiet, it is not resting, it is moving, stretching, dragging every star, every galaxy, every atom, farther away from every other. The universe is not a static painting. It is a living, breathing, expanding thing, and it is expanding far faster than it should. From the moment you were born, every second of your life has taken place on a cosmic conveyor belt you can never step off. Even as you sleep, galaxies are rushing away at incomprehensible speeds. Distances between clusters swell. Light itself struggles to cross expanding space. The very fabric of reality beneath you is being pulled apart. And here is the part that should unsettle you. We thought we understood this expansion. We thought we had it measured, labeled, solved. For decades, cosmologists believed the universe behaved predictably, that space grew at a calculable rate, that its past, present, and future could be charted with confidence. We carved its numbers into textbooks. We taught them to students as if they were laws. Then something broke. We began to measure more carefully, with more powerful telescopes, more refined instruments, more precise mathematics. Humanity stared deeper into the cosmos than ever before, and the universe stared back with a contradiction. Two of our best, most trusted cosmic rulers, our greatest tools for measuring the heartbeat of the cosmos, do not agree on how fast the universe is expanding. Not by a small amount, not by a rounding error, enough to fracture our understanding of reality. This is not a small embarrassment for science. This is not a glitch easily explained away. This is a silent scream coming from the fabric of existence, whispering that something is fundamentally wrong. You live inside a universe that refuses to obey its own rules. Every galaxy is trapped in this unstoppable outward surge. Imagine entire cities of stars drifting apart, great islands of matter tearing away from one another in an endless ocean of darkness. Gravity, the great binding force, is losing. Expansion is winning. The cosmos is not settling into tranquility. It is accelerating. It is racing. Like a storm that should have slowed long ago, but instead grows louder. And unlike the familiar movement of planets orbiting suns or moons circling worlds, this isn't motion through space. This is motion of space. Space is stretching. The cosmic stage itself is widening, and everything upon it is being dragged along. For a moment, consider what that means for you. Every breath, every heartbeat, every human memory is etched into a universe that is literally slipping apart beneath it. Stars will one day drift too far to see. Galaxies that shine above you tonight will vanish beyond a horizon where their light can never reach us again. Future civilizations will look up and find emptiness, a blank black ceiling. They will never know the universe once burned bright. But the dread lies not in the future alone. The dread lies in right now, in the present, in the cruel uncertainty of not understanding why this is happening. Because when you find disagreement at the foundation of physics, you are forced to face a horrifying possibility. We may not truly understand the universe we are living in. And if we don't understand it, how can we trust it? We sit on a fragile rock, orbiting an ordinary star, drifting inside a galaxy, racing through cosmic darkness. And even the scientists who devote their lives to understanding this vastness are now staring at data that should not exist. They expected certainty. They found contradiction. They expected clarity. They found mystery. They thought the cosmos was solved. It was not. The universe is expanding too fast, and physics might be wrong. This is where the unease begins to take root, deep in the back of the mind, in the quiet places we avoid thinking about, because we want the universe to be stable, predictable, lawful. We need it to make sense, but the cosmos does not care about our comfort. It does not owe us simplicity. It does not promise to behave. There is a specific number that defines the expansion of the universe, a number that should be absolute, fixed, unquestionable. It is known as the Hubble constant. It is the measure of how fast galaxies retreat from one another. For decades, scientists have worked tirelessly to refine this number, believing that once we truly understood it, the universe would finally reveal its story. But now, two different cosmic measurements produce two different universes. One whispering from the infancy of creation, another echoing from the present day, and neither one willing to match the other. Imagine building a bridge and discovering halfway that the measurements of one end do not agree with the measurements of the other, that the blueprint contradicts itself, that you cannot trust your own ruler, that everything you calculated might collapse. This is no longer just a scientific inconvenience. This is a crack in the foundation of reality. Something is wrong with our understanding of space, time, or energy. Something is wrong with the equations that describe existence. Something perhaps is wrong with reality itself. And the most terrifying part, the universe isn't explaining itself. It continues to expand, faster, relentless, indifferent to whether we understand or whether we ever will. Somewhere out there, beyond the stars, beyond the cosmic web of galaxies, beyond the cold gravitational skeleton of everything that exists, lies the truth. But the universe is not making it easy to find. We may be witnessing the limits of human comprehension, standing at the edge of cosmic understanding, staring into a mystery that refuses to resolve. Because when the most fundamental measurements of reality disagree, when the cosmos itself sends conflicting messages, it forces us to ask a question humanity has avoided since the beginning. What if the universe we live in is not the universe we think it is? And if we are wrong about this, what else are we wrong about? The story of the Hubble tension begins here, with a universe expanding too quickly, with reality slipping out of our grip, and, with a haunting realization, we might be living inside a broken equation. Welcome to the problem that keeps cosmologists awake at night. Welcome to the quiet panic spreading through astrophysics. Welcome to a universe that won't sit still. There was a time when the universe felt knowable. Not because it was small, not because it was simple, but because for the first time in human history, we had a story that fit together. A story with a beginning, a middle, and an ending that, while bleak, was at least coherent. We had equations that didn't just describe what we saw, they predicted what we would see next, and the predictions kept coming true. It was intoxicating. For most of our existence, the cosmos was mythology, a ceiling of gods, a tapestry of omens, a place where meaning was projected because meaning was needed. But then, slowly, we began to replace the old stories with measurements, telescopes, spectra, photons caught after traveling for billions of years. We stopped asking what the sky meant and started asking what it was made of, and the sky answered. In the early 20th century, the universe cracked open, not with fireworks, but with numbers. Astronomers noticed something strange in the light of distant galaxies. Their spectral lines, those thin fingerprints of atoms, were shifted, stretched toward the red end of the spectrum. Redshift, a subtle cosmic signature that said with cold clarity that galaxies were moving away from us. At first, it sounded like a mistake, or an optical illusion, but the further astronomers looked, the stronger it became. The more distant the galaxy, the faster it receded. Not randomly, not chaotically. With a brutal linear order, the universe was expanding. That single realization changed everything. Because expansion implies a past that was smaller, denser, hotter. A past where the galaxies were not scattered like islands in an endless ocean but packed closer together in a cosmic crowd. Rewind the film of expansion far enough, and the crowd becomes a crush. Rewind further, and space itself becomes a furnace. The universe becomes an early state so extreme that matter and light blur into a single violent plasma. This was the birth of the Big Bang picture, not as a literal explosion into space, but as the expansion of space from an early hot dense condition. A universe that began not with matter flying outward through emptiness, but with emptiness itself unfurling, carrying matter along for the ride. Then came the smoking gun, a faint glow discovered in the 1,960 seconds, microwave radiation filling the sky in every direction. Not coming from a particular star or galaxy, but from the entire universe itself. The afterglow of the early cosmos, cooled by expansion, stretched into microwaves by the passage of time. The cosmic microwave background. It was like hearing the universe's first cry, still echoing, still everywhere, a whisper from when reality was young enough to burn. And with that whisper, the story sharpened. The cosmic microwave background wasn't perfectly smooth. It had tiny fluctuations, minute differences in temperature across the sky, little ripples, little scars. They were impossibly small, but they mattered, because those ripples were the seeds, the slight imbalances that gravity would later amplify into galaxies, clusters, and the cosmic web. They were the blueprint of everything that would ever exist. The universe, it seemed, had left us its schematics. For a while, cosmology became a rare kind of science, a field that could test the untestable, a discipline that tried to reconstruct an origin story older than Earth, older than the sun, older than the atoms in your bones. And astonishingly, the reconstruction worked. The math held. Observations snapped into place like gears meshing. A simple framework emerged, elegant enough to fit on a slide, powerful enough to describe the largest thing we will ever try to understand. It went by a name that sounds sterile, almost insulting to its importance, the Standard Model of Cosmology. A universe made of ordinary matter, everything you can touch, everything you are only a small fraction of the whole. A universe also made of invisible mass we cannot see but can measure through its gravity. Dark matter, the unseen scaffolding that holds galaxies together and shapes the cosmic web. And a universe filled with something even stranger, a force driving acceleration. Dark energy, not a substance you can bottle, not a field you can point to in a lab. A name we gave to the behavior of space itself. The universe was not just expanding. It was expanding faster over time, as if some hidden pressure was pushing outward from every point in existence. Put together, it was a cold, unsettling recipe. You are made of the rarest ingredient, but even that felt stable. Because the model explained so much. It explained the microwave background. It explained the distribution of galaxies. It explained the abundance of light elements forged in the first minutes of existence. It explained why the cosmos looks the way it does on the grandest scales. Cosmologists began to speak with confidence. They refined parameters. They argued over decimals. They fought over the seventh digit after the point. And from the outside, it looked like the end of mystery, as if the universe had finally been cornered, as if all the deep questions were now just engineering problems. This was the era of cosmic certainty. But certainty is a dangerous drug because it makes you forget what you are doing. You are trying to understand a universe that contains black holes, regions where space curves so violently that time slows to a crawl where the future ends at an event horizon. You are trying to understand a quantum world where particles exist in superposition, where causality becomes a probability cloud, where the act of measurement seems to decide what is real. You are trying to understand a cosmos that began in conditions so extreme we can't recreate them and may end in ways we can barely name. In a universe like that, any confidence should feel suspicious. Still, for a while, the model worked. It worked so well that it began to feel inevitable. Like the universe had always been waiting for us to discover it. Like the cosmos wanted to be understood. Like the math was not just a description but a truth. And then, quietly, the first cracks appeared. Not loud, not dramatic, not obvious to anyone outside astrophysics. Just a number that should have been the easiest part. Because if you know the model, if you know what's in the universe and how it behaves, you can predict how fast it should be expanding today. And if you can measure how fast it is expanding today, you can test whether your story is correct. This is where cosmology becomes a kind of interrogation. The early universe speaks through the microwave background, through ancient light, through patterns frozen in the oldest radiation we can see. The late universe speaks through galaxies, supernovae, stars, and the cosmic distances close enough for our instruments to resolve. These should be two perspectives on the same reality. Two cameras filming the same event from different angles. They should match. But the more precise we became, the less they did. One method said the universe is expanding at one rate. Another said it is expanding at a different rate. And at first, everyone did what humans always do when reality doesn't fit. They assumed the universe was fine and the humans were wrong. They blamed calibration. dust, instrument error, statistical flukes, a minor mismatch that would vanish with more data. Except it didn't vanish. It grew sharper. It grew harder, like a hairline fracture in a windshield spreading across the glass, thin at first, then branching, then impossible to ignore. And suddenly the thing that looked like cosmic certainty started to feel like cosmic denial. Because when the universe tells you two incompatible stories, you are forced to confront an idea that is both terrifying and beautiful. Either something is wrong with our measurements, or something is wrong with the universe we thought we understood. This is the moment cosmology changes from a solved puzzle into a horror story. Not because the universe becomes less wondrous, but because it becomes less trustworthy. Because the laws we relied on, the equations we treated as sacred, might only be approximations, temporary rules, local truths in a bigger, stranger reality. We thought we had mapped the cosmos, but now the map and the territory are diverging, and somewhere in that divergence something is hiding, something that could rewrite our story of existence. To say the universe is expanding is easy. To prove it is an act of obsession. Because the cosmos does not hand you a measuring tape, it gives you only light, thin, ancient messengers that have crossed gulfs so large they mock the word distance. Every photon we catch is a survivor. It has endured billions of years of empty travel, slipping between galaxies, passing through dust, bending around gravity, sometimes arriving so faint that it barely qualifies as a signal at all. And yet we ask it to carry the weight of the biggest measurement in existence. How fast is reality stretching? The universe doesn't answer with a voice. It answers with a shift. Light is a kind of code. Split it with a prism, and you get a spectrum colors, yes, but also a set of dark lines where specific wavelengths are missing. Those gaps are not errors, they are signatures. Every element absorbs and emits light in its own pattern. Hydrogen leaves one fingerprint, oxygen another, iron another, a chemical barcode embedded in starlight. Now imagine that barcode arriving from a distant galaxy, but the lines are moved, not just a little blurred, moved, stretched toward longer wavelengths toward the redshift. It is the universe's simplest confession: the light has been stretched because space itself stretched while the light traveled. The photon did not merely move through a static void. The void lengthened beneath it, pulling the wave apart like taffy. The more space expands during the photon's journey, the redder the light arrives. Cosmologists quantify this stretching with a symbol that looks harmless: Z. Redshift Z is a ratio, a measure of how much the universe has expanded since the light left its source. A galaxy with Z equals 1 is seen when the universe was half its current size. A galaxy with Z equals 2 is seen when the universe was a third of its current size. Higher Z means deeper time, deeper past, closer to the early furnace of creation. Redshift tells you the expansion happened, but to turn that into a speed you need something else. You need distance. And distance is where the dread begins, because distance in the universe is never direct. We cannot reach out and touch a galaxy. We cannot stretch a tape measure across intergalactic space. Everything is inference. Everything is built on a ladder of assumptions, stacked on top of other assumptions, each rung trembling under the weight of the next. This is what astronomers call the cosmic distance ladder. It starts close, where we can be confident. In our neighborhood of the Milky Way, we can measure distances through geometry parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background. It is the same trick your brain uses for depth perception. A tiny angle becomes a distance. Simple, clean, almost comforting. But parallax dies quickly. Beyond a certain range, the angles become too small. The universe outgrows your geometry. So you climb the next rung. You look for objects whose brightness changes in a predictable way, like a lighthouse with a known bulb. Cepheid variable stars are one of the great gifts of astrophysics: stars that swell and contract, pulsating rhythmically. The key is that their period is tied to their intrinsic luminosity. Measure how fast they pulse, and you know how bright they truly are. Compare that true brightness to how dim they appear, and you get distance. Distance becomes a brightness problem, a light fall-off problem, a cosmic guessing game where you win only if your assumptions about the source are correct. Cepheids can carry you to nearby galaxies, but not far enough, not across the universe. The ladder must climb again. And here we meet the candles that light the modern cosmic crisis. Type Ia supernovae. These are not ordinary explosions. They are catastrophic thermonuclear deaths, often involving a white dwarf, an ember of a star compressed to near the limits of matter, a sphere of carbon and oxygen packed so tightly that a teaspoon would weigh as much as a mountain. In some systems, the white dwarf steals material from a companion star. It grows heavier, tighter, more strained, until it approaches a critical threshold. Then in a runaway fusion reaction, it detonates. The reason cosmologists love Type Ia supernovae is that they are remarkably consistent. They shine with nearly the same intrinsic brightness each time, like cosmic flares with a standardized intensity. Not perfect, never perfect, but consistent enough to serve as standard candles. Standard candles are sacred in astronomy. They let you measure distance across billions of light years. They extend the ladder to the scale where the universe itself becomes the laboratory. Here is the grim beauty of it. You observe a supernova in a galaxy. You record its light curve, the way its brightness rises and falls. From that curve, you infer its intrinsic luminosity. You compare it to its apparent brightness. You calculate distance. Then you measure that galaxy's redshift. Distance and redshift together let you estimate expansion. Do this for many galaxies across the sky, and you build a relationship. The farther the galaxy, the greater the redshift. The universe is stretching, and the slope of that relationship reveals the Hubble constant, the expansion rate today. This is the late universe method, the local measurement. Not local as in your neighborhood, but local as in the relatively nearby cosmos compared to the ancient microwave background. This method relies on the distance ladder parallax to Cepheids to supernovae, each rung calibrated by the one beneath. If you hear a faint unease in this, you are hearing it correctly, because the distance ladder is not a single measurement. It is an interlocking chain, and chains can snap at weak links. Is the parallax calibration perfect? Are Cepheids truly universal, or do their properties shift subtly with metallicity, age, environment? Do supernovae explode with exactly the same brightness everywhere, or does their light depend on hidden factors we don't fully understand? Does cosmic dust dim them? Does the host galaxy bias the sample? Are we unknowingly selecting cleaner, brighter events and ignoring the messy ones? Every one of these questions is a potential trapdoor. And yet, for decades, the trapdoors didn't open. The results converged, the ladder stood, the universe seemed measured, until the precision became too sharp to forgive. As telescopes improved, as surveys multiplied, as the statistics tightened, the local measurement of the Hubble constant crept upward. Not wildly, not chaotically, with a disturbing consistency. It insisted the universe is expanding faster than the early universe picture predicts. And that is the nightmare. Because the local measurement isn't just a single team or a single telescope. It is an entire ecosystem of independent observations, refining each rung, cross-checking each other, hunting for systematic errors like detectives combing a crime scene for the hidden weapon. And still, the number stays high. The late universe looks at us and says the expansion rate is faster, which means either our ladder is subtly crooked, or the universe itself has changed its behavior between infancy and now. That second possibility is the one that makes your stomach drop, because it suggests the cosmos is not governed by a single set of timeless laws, but by evolving rules, rules that may shift over cosmic history. Dark energy that isn't constant, gravity that doesn't behave the same on all scales, unknown fields that awaken and fade. It suggests the universe has a secret phase we didn't account for. Or worse, it suggests there is something fundamentally missing from our story, something so basic that it hides in plain sight, warping our measurements without revealing its face. And if we can't measure the universe's expansion reliably, if the ruler itself is suspect, then the entire cosmic timeline becomes uncertain. The age of the universe, the fate of the universe, the meaning of the cosmic microwave background's patterns, all of it rests on this foundation of distance and redshift, on the careful dance of light and inference. It is unsettling to realize that our greatest cosmological discoveries are built not on direct touch but on trust. Trust in the behavior of stars, trust in the repeatability of explosions, trust in the assumption that light is honest. But what if the light is telling the truth, and the truth is that our physics is incomplete, because there is an even darker thought buried inside the distance ladder, a thought that doesn't show up in equations but haunts them anyway. If the universe can mislead our measurements this profoundly, then perhaps reality is not obligated to be transparent. Perhaps the cosmos is not built to be understood from within. Perhaps any civilization, no matter how advanced on the Kardashev scale, no matter how many stars it cages, no matter how many galaxies it harvests, will still face the same problem. The universe can expand, evolve, and conceal its deepest mechanisms behind curtains of distance and time. We are trying to measure an ocean while trapped inside a droplet. And the droplet is evaporating. The cosmic distance ladder is humanity's attempt to fight that confinement step by step, rung by rung, reaching outward into the dark with instruments that translate faint light into meaning. But now the ladder is pointing at something unsettling, a number that refuses to match the number whispered by the early universe. A disagreement carved into the sky itself. And in the next part, we will listen to the oldest light in existence, the universe's first fossil, because it tells a different story. A story so precise, so consistent, so beautiful, that the contradiction becomes even more terrifying. Because when the early universe speaks, it does not stutter. It sings, and it sings the wrong number. If the late universe is a messy crime scene, the early universe is a confession recorded in perfect silence. It is the oldest light we will ever see, older than stars, older than galaxies, older than the atoms in your blood. A faint uniform glow that fills all of space, coming from every direction at once, so evenly spread across the sky, that it feels less like something out there and more like something you are inside of. This is the cosmic microwave background. Not a metaphor, not a philosophical idea, actual photons, actual light, still traveling, still arriving, still carrying information from a time when the universe was young enough to be hot in every direction like a single enormous fire. There was a moment in the ancient cosmos, roughly 3,800,000 years after the beginning, when space had cooled enough for electrons to finally bind to nuclei. Before that, the universe was opaque. A glowing plasma where light could not travel far without being scattered. Photons were trapped in a dense charged fog, bouncing endlessly, unable to escape. The cosmos was bright but blind. Then the temperature fell. Electrons settled, neutral atoms formed, and suddenly the universe became transparent. Light was released. Those photons have been traveling ever since, stretched by expansion, cooled by time, redshifted down from searing early radiation into microwaves so faint you would never feel them. They pass through you right now, through your skin, your skull, your eyes' ghosts, from an era when the universe was still learning what space even meant. This light is not just old, it is a fossil. And like all fossils, it carries a record of the conditions that created it, not written in letters but in temperature. Tiny fluctuations across the sky, differences so small that in absolute terms they are almost insulting. 1 part in 100,000, a barely perceptible mottling in a sea of near-perfect uniformity. And yet those tiny differences are everything. They are the fingerprints of primordial physics, the imprint of pressure waves that rippled through the infant universe. Yes, sound. Not sound in air, but sound as oscillations in the hot plasma itself. Regions of slightly higher density, pulled inward by gravity. Radiation pressure pushed outward. The tug of war created waves swelling and collapsing across space, like the universe was ringing like a bell. These are called baryon acoustic oscillations, and you can think of them as the universe's first rhythm, gravity and pressure beating against each other in a newborn cosmos. When the universe became transparent, that rhythm froze in place. The waves stopped evolving because the medium changed. The plasma vanished into neutral gas, and the sound died. But the pattern remained locked into the microwave background as a set of ripples we can measure today. This is where the dread intensifies, because the cosmic microwave background is not vague. It is not poetic, it is not ambiguous. It is an extraordinarily precise map, a dataset so rich that it feels almost unfair, like the universe accidentally left the door open and we glimpsed the machinery inside. The Planck satellite was one of the great instruments built to read this fossil light. It measured the microwave background with exquisite sensitivity, charting the tiny temperature fluctuations across the sky. It turned the universe's oldest glow into numbers, into curves, into peaks and valleys that encode the basic ingredients of existence. Those peaks, called acoustic peaks, are not just shapes, they are constraints. They tell you how much ordinary matter there is, how much dark matter, how curved space is, how the early universe expanded, how fast it cooled. The microwave background doesn't merely suggest these things. It corrals them, corners them, forces them into a narrow range. From this one ancient snapshot, cosmologists can infer a complete cosmological model, a universe that begins hot and dense, expands, forms structure, and accelerates under dark energy. And within that model is an implied expansion rate today. This is the crucial point. Planck does not directly measure the Hubble constant in the present. It measures the early universe with terrifying precision. Then, using the standard model of cosmology, our best set of equations, describing how the universe evolves, it projects forward to predict what the expansion rate must be now. It is like reading an embryo's DNA and predicting the adult. If the model is correct, the prediction should match the late universe measurement. If the prediction does not match, either the late universe measurement is wrong, or the model is missing something fundamental. Planck's prediction within the standard cosmological framework is lower. The early universe whispers a calmer expansion rate. A universe stretching, yes, but not as violently as the local measurements insist. And here, the contradiction takes on a new, colder shape, because the Planck data is not easy to dismiss. It is internally consistent to a degree that feels almost supernatural. The patterns it measured align with other cosmic relics too, like the large-scale distribution of galaxies and the imprint of those primordial sound waves on matter itself. The early universe, as seen by Planck, behaves like a masterpiece of mathematics. A cosmos that can be modeled, simulated, and predicted with shocking success. And yet, when that early universe story is marched forward into the present, it lands on a different number than the one measured by the distance ladder. Two methods, two time eras, two expansion rates, one universe. This is why the Hubble tension is not just an argument about decimals. It is an argument about the continuity of physical law across time itself. Because if the early universe is telling the truth and the late universe is telling the truth, then the laws connecting them are wrong. Something happened between then and now. Some hidden event, some shift in the behavior of dark energy, some change in the strength of gravity, some exotic component that mattered in the early universe but faded away like a phantom influence that pushed the cosmic story off course. The standard model assumes that dark energy behaves like a constant, the same everywhere, the same always, a steady pressure built into the structure of space-time. But what if it isn't constant? What if dark energy has a history? What if it had a different strength in the early universe, or it evolves, or it interacts with other components we have not detected? What if the universe has an internal clock we didn't know existed? Because the microwave background doesn't just give us a number, it gives us a demand. If you want to keep the early universe's picture intact, then the late universe's faster expansion becomes a kind of accusation. It says, your model is missing a chapter, and there is a nightmare hidden in that idea. In physics, missing a chapter often means missing an entire kind of reality, a new field, a new particle, a new interaction, a new degree of freedom in the cosmos, something that exists not in the margins but in the foundations, something so pervasive that it shapes cosmic expansion itself and yet remains invisible to our direct detection, hiding behind gravity and time. It is unsettling because we have been here before. We once thought Newton's gravity was complete until Mercury's orbit misbehaved and forced us into Einstein's warped space-time. We once thought the Milky Way was the entire universe until we learned the sky is filled with other galaxies. We once thought atoms were indivisible until they cracked open into quantum storms. Each time the universe didn't merely add a detail, it changed the rules. So when Planck's ancient light suggests one expansion rate and the late universe insists on another, it feels like the beginning of that pattern again. A small discrepancy that could be the first tremor of a conceptual earthquake. And if the rules can change once, they can change again. Now, let the thought sharpen. If the Hubble constant is not constant, if expansion behaves differently than our model predicts, then the age of the universe becomes less certain. The timeline of structure formation becomes less certain. Even the fate of the cosmos becomes less certain because the future depends on the same physics that is now under suspicion. Our cosmic story could be wrong at the level of its backbone. We might have built a cathedral of understanding on a foundation that is quietly shifting, and there is another darker layer to this. The cosmic microwave background is not just a relic of the past, it is also a boundary to our knowledge. It marks the limit of direct observation. Before that era of transparency, the universe is essentially hidden, opaque. We can infer what happened earlier, but we cannot see it with light. There is a veil in the sky, and beyond that veil may be physics we do not yet understand. So when the early universe measurement disagrees with the late universe, it feels like the veil is tugging back, like the cosmos is reminding us you do not get to see everything. You do not get to know everything. You are a small intelligence trapped inside a vast, expanding system, trying to understand it from a single perspective in time and space. Planck gave us a beautifully coherent story of the infant universe, but it also gave us a haunting warning. Because if the infant universe is that precise, that clean, that mathematically obedient, then why does the adult universe refuse to match? In the next part, we will finally name the contradiction in full. We will place the two numbers side by side and feel the chill of their disagreement. Because once you see how far apart they are, once you realize how hard the community has tried to reconcile them, you begin to understand the real terror of the Hubble tension. This might not be an error. This might be the universe telling us the standard story is incomplete. And when the standard story is incomplete, the unknown is not at the edges. The unknown is at the center. If the cosmic microwave background is a message from infancy, the nearby universe is the adult speaking back, and the adult is agitated. Because while Planck listens to the ancient afterglow and predicts a calmer expansion, the late universe measured with stars, you can resolve explosions, you can watch unfold galaxies close enough to map in detail, keeps insisting on something, faster, not subtly faster, uncomfortably faster. As if the universe has been quietly pressing down on the accelerator when no one was looking. This is where the Hubble tension stops feeling abstract. It becomes personal. It stops being a debate about early universe modeling and becomes a confrontation with the sky you actually see. The galaxies in our cosmic neighborhood carry redshifts that are small compared to the deep past, but they are honest in a different way. Their light has not traveled from the edge of time. It has traveled from a place the human mind can almost imagine as near, and yet their recession measured again and again still does not align with the number whispered by the primordial universe. The method is elegant, almost cruel in its simplicity. Find something whose true brightness you can infer. Compare it to how bright it looks. Turn that into distance. Then read the galaxy's redshift like a speedometer. And when you do this across enough galaxies, you can feel the universe stretching in your hands. Cepheid variables are the first heartbeat in this chain. They brighten and dim with a regular pulse like a signal lamp in the dark. Their period reveals their intrinsic luminosity. That makes them a bridge close enough to calibrate with geometry bright enough to be seen in other galaxies. They are the stepping stones across intergalactic space. But Cepheids don't take you far enough on their own. You need something brighter, something that can be seen at the edge of the local universe beyond the reach of individual stars. That something is death. Type Ia supernovae. They flare up with the brightness of an entire galaxy, then fade. For a brief window, they become beacons visible across enormous distances. They are the universe's most violent measuring sticks, explosions repurposed as rulers. The distance ladder, rung by rung, turns the late universe into a grid of inferred distances. And then the redshift measurements, those stretched spectral fingerprints, turn those distances into an expansion rate. This is the local Hubble constant, the universe's present-day tempo, and it refuses to slow down to match the early universe. For years, teams have refined this ladder until it resembles something almost surgical. They hunt down every potential distortion dust that dims light biases in which galaxies get chosen. Subtle differences in star populations, calibration, drifts in detectors. They argue over the smallest details because the smallest details are where the truth hides. And then the numbers come out, and the truth feels worse. The local measurements built on Cepheids and Type Ia supernovae keep landing in the low 70 seconds kilometers per second per megaparsec, a number that sounds harmless until you realize what it means. For every megaparsec of distance, the recession speed climbs by that amount. Over hundreds of megaparsecs, you get thousands of kilometers per second. Over cosmic scales, you get a universe that cannot hold itself together as one connected place. A universe that is actively abandoning its own structure. This higher value doesn't come from one fragile dataset. It has survived multiple generations of telescopes and analyses. It has been attacked from every angle, and it keeps coming back. Then the skepticism deepened, as it always does in science, because skepticism is the only thing that stands between truth and self-deception. What if Cepheids are the problem? They live in crowded stellar neighborhoods. They glow amid other stars, and if your telescope cannot perfectly separate them, their brightness can be contaminated, artificially brightened. If they look brighter than they truly are, they seem closer than they are, and that ripples upward through the ladder, inflating the expansion rate. So astronomers tried to sharpen their vision, not with philosophy, with better eyes, higher resolution, better infrared observations, cleaner separation of stars from the haze of their host galaxies. The goal was brutal: remove the messiness of real astrophysical environments from the measurement. And this is where a new instrument enters like a scalpel: James Webb. With its infrared vision and sharp resolution, Webb can peer into dusty regions and crowded fields with a clarity that older observatories struggled to achieve. It can resolve stars where the past saw blur. It can reduce the very kinds of systematic uncertainty that critics hoped would dissolve the tension. And the uncomfortable twist is that improving the measurement hasn't erased the disagreement. It has, in many cases, made the disagreement harder to dismiss. Not because Webb proved one side right forever, no telescope delivers that kind of finality, but because the act of cleaning up the ladder hasn't cleanly dragged the local Hubble constant down to meet the early universe. The ladder is being reinforced, not abandoned. Still, scientists don't trust a single ladder when the stakes are this high. They build new ones. Another method uses a different kind of stellar landmark, the tip of the red giant branch. In old stellar populations, red giants reach a maximum brightness before helium ignition changes their structure. That maximum can serve as another standard candle: different physics, different systematic errors, different vulnerabilities. Some measurements using this approach have tended to land lower than the Cepheid supernova ladder, closer to the high 60 seconds or around 70, as if the universe is offering a compromise number that satisfies no one completely. And then there are still more attempts to escape the ladder entirely. Strong gravitational lensing time delays, where light from a distant quasar takes different paths around a massive foreground galaxy, can encode absolute distances through the geometry of space-time itself. The paths differ, so the arrival times differ. Measure the delays, model the lens, and you can infer the cosmic scale. It is a method that feels almost mythic. Time itself becomes the tape measure. And the results across different lensing analyses have sometimes leaned high to another late universe voice that won't neatly collapse into the early universe prediction. So the late universe becomes a chorus. Cepheids and supernovae speak. Red giant branch stars speak. Lensed quasars speak. And they do not sing in perfect harmony, but they keep circling a region of values that refuses to settle cleanly on the early universe number. This is why the tension feels like a genuine fracture rather than a minor disagreement. Because if it were only one approach, only Cepheids, only one survey, only one group, you could point to it and say, there, That's the weak link. That's the rung that's cracked. But the late universe is not offering a single weak link. It is offering persistent discomfort across multiple partially independent probes. And in the background, the early universe remains infuriatingly coherent. It continues to fit a clean model with a clean history, as if the cosmos is daring us to accuse it of being inconsistent. So which is it? Is the late universe lying because our distance ladder is subtly warped? Or is the early universe telling the truth under assumptions that are just barely wrong? Because that's the key, the early universe value is not measured directly as expansion today. It is inferred through a model. It is the adult predicted from the infant. And if the adult doesn't match, maybe the model of growth is incomplete. At this point, the Hubble tension stops being about telescopes and becomes about time. It becomes about whether the laws of the universe are stable from one era to another, whether dark energy behaves the same way in every epoch, whether gravity is truly what we think it is on the largest scales, whether there are hidden ingredients, fields, particles, interactions that existed in the early universe and then faded like a ghost, leaving fingerprints only on cosmic expansion. Because the alternative is almost worse in a quieter way. The alternative is that our ability to do cosmology is fundamentally limited from within, that we are trapped inside a system whose deepest properties cannot be cleanly measured because every measurement is distorted by assumptions we cannot step outside of. We are trying to measure the universe while standing inside it using tools made of the universe, calibrated by phenomena that themselves are shaped by cosmic history. At the smallest scales, physics speaks in the language of the Planck length, space, chopped into an almost unimaginable granularity where our theories begin to dissolve into silence. At the largest scales, physics speaks in redshift and cosmic distance, where our theories also begin to dissolve not into granularity but into ambiguity. The universe is too small at one end, too large at the other, and the Hubble tension lives right in the middle, where our confidence was supposed to be strongest. In the next part, we will face the contradiction head-on, not as a poetic unease, but as a mathematical impossibility that has survived years of scrutiny. Because once you place the early universe value and the late universe value side by side, you start to feel the deeper horror of it. These are not just two different numbers. They are two different realities. And both realities are being measured by people who have built machines precise enough to hear the universe whisper. So why is the universe telling two different stories? And what kind of universe does that imply we're living in? In science, disagreement is normal. It's the engine, the friction that grinds rough ideas into sharper ones. Two experiments return two values, and you don't panic, you look for error bars. You look for calibration drift. You look for the tiny human ways reality gets smeared by instruments and assumptions. Most disagreements die quietly resolved by better data or revealed as noise masquerading as meaning. But sometimes a disagreement refuses to die. Sometimes the numbers don't just disagree, they harden. They become stubborn. They sit there like a bruise on the body of physics, darkening the more you touch it. That is what makes the Hubble tension feel different. It is not just that two methods produce two answers. It is that those answers are separated by an amount that should have collapsed by now if the universe were as well behaved as we hoped. The uncertainty has shrunk. The measurements have improved. The analysis pipelines have been attacked and rebuilt, and the gap remains. At first, you could shrug and say it's early days. We're still learning how to measure the cosmos properly. We are a young species with young instruments. We should expect the universe to look inconsistent while our methods mature, but the tension has been maturing with us. It has been marching upward in statistical significance as the data becomes more precise, like the universe is not merely allowing the contradiction, it is sharpening it. This is the part that makes cosmologists uneasy in a way that doesn't show up in press releases. Because statistical significance is the language scientists use to decide when an anomaly becomes a crisis. A few sigma is a raised eyebrow. 3 sigma is a serious conversation. Approaching 5 sigma is when people stop joking and start rewriting grant proposals. The Hubble tension has edged into that territory, not in one dramatic leap but through years of quiet accumulation, like a verdict forming from endless small pieces of evidence. It is still debated how to quantify it, different datasets, different treatments, different assumptions, but the direction is hard to ignore. The more carefully you listen, the more the universe sounds like it is saying no, your story does not close. And what makes it terrifying is what the disagreement represents. It isn't merely a mismatch of one parameter, it's a mismatch between eras. The early universe is a place we cannot return to, a time we can only reconstruct through relic light. The late universe is the present, the cosmos we can measure with stars, explosions, and geometry. These two domains are connected by the assumption that physics is stable, that the same laws that governed the infant cosmos carried it faithfully into adulthood. The Hubble tension is the universe testing that assumption. It is the cosmos asking us with numbers instead of words, "Are you sure the rules didn't change?" Because if the rules did change, then the consequences spill everywhere. The Hubble constant is not an isolated knob you can tweak without touching anything else. Cosmology is a web. Pull one thread and the pattern shifts. If the expansion history is wrong, then distances change, ages change, the inferred amount of matter changes, the growth of structure changes. Even the shape of the cosmic web, the very way galaxies gathered into clusters, becomes a new problem. So the tension becomes a question of trust. Do we trust the late universe's distance ladder, a towering construction of calibration, one rung resting on the next, each step demanding that stars and explosions behave reliably across time and space? Or do we trust the early universe's fossil record, a relic glow that seems internally consistent to a frightening degree, but whose translation into today depends on the correctness of the model we use to evolve it forward? It is like having two witnesses to the same event, one speaking from childhood, one speaking from adulthood, and realizing their stories cannot both be true unless something happened in between that neither of them is telling you. And then comes the most haunting possibility. What if both are true? What if the universe is not inconsistent, only our description of it is? Because that is exactly what new physics looks like at first, a mismatch between equally credible measurements. An old framework that fits most of the data perfectly until one stubborn corner refuses to align. The refusal isn't random. It has a shape, a direction, a persistent insistence. In the history of science, these are the moments that matter. A planet's orbit deviates slightly. A constant appears not to be constant. A spectrum contains unexpected lines. A tiny anomaly becomes the crack that reveals a deeper structure underneath. But the Hubble tension is uniquely unsettling because it is not a small anomaly about a small thing. It is an anomaly about the universe's scale itself, about the metric that tells you how big things are and how far back time goes. It is a disagreement about the geometry of existence. And geometry is not supposed to be negotiable. If you ask most people what space is, they imagine emptiness, a passive stage, a void where things happen. But modern physics insists space is not passive. Space is dynamic. It has a shape. It can stretch and curve and ripple. It can be warped by mass and energy. It can behave like an object with properties of its own. And now we are faced with the idea that space's behavior might not be fully captured by the equations we rely on. This is the part where dread slips in because the viewer realizes the problem is not a technical quibble. It is a philosophical fracture. If our best measurements of the universe's expansion disagree, then we do not have a complete account of what reality is made of. Not at the margins. At the core, the universe becomes less like a solved machine and more like a living mystery, something with hidden compartments. And hidden compartments are where nightmares live, because hidden compartments imply hidden mechanisms, forces that act without revealing themselves. Fields that influence the cosmos without leaving a straightforward trace. Particles that were abundant in the early universe but became rare and silent later, like extinct creatures whose bones still shape the landscape. There is a kind of cosmic horror in that thought that the universe could contain entire categories of existence that mattered deeply and then vanished, leaving behind only a subtle mismatch in a number, a faint distortion in how fast galaxies flee. It is also still possible that the late universe measurements are wrong in some subtle, systematic way, that the ladder is leaning, that the light is biased, That dust crowding, evolution, or selection effects are conspiring to inflate distances or deflate them, nudging the expansion rate upward. But if that is the case, the universe is forcing us to accept another uncomfortable truth, that even our best instruments may be seduced by invisible biases, that we may be calibrating the cosmos with candles whose flames are not as standard as we believed. And if our measurements are vulnerable to hidden bias at this scale, then the entire project of cosmology, of reconstructing the universe's history from within, becomes haunted by uncertainty. It becomes a discipline where the universe is always one step ahead, always capable of hiding behind the complexity of its own contents. Yet, if the early universe inference is wrong, the implications are even more destabilizing, because then the standard model, this elegant framework that has guided decades of cosmic understanding, is incomplete. Not incomplete in the way a textbook is incomplete, missing a few footnotes. Incomplete in the way a map is incomplete when an entire continent is missing. And missing continents have consequences. Because the early universe is where physics becomes extreme, it is where densities and energies climb toward regimes we cannot recreate. It is where the smooth laws of general relativity begin to feel fragile. It is where quantum mechanics, so strange already, might become the dominant language of space-time itself. At that boundary, the Planck length waits like a cliff edge, a scale so small that our notions of distance and continuity may dissolve. The universe may not be made of smooth fabric at all. It may be granular, quantized, a foam of space-time fluctuations. And if the universe's deep structure is not smooth, if space-time itself has hidden behavior, then the expansion history could be influenced in ways our current models cannot capture. The Hubble tension might be the first outward symptom of that deeper truth, a minor fever revealing a body we do not fully understand. This is where the disagreement becomes existential, because the expansion rate is not just a number, it is the metronome of the cosmos. It sets the scale of everything we infer: how old the universe is, how long galaxies have had to form, how quickly structure grew, how far away the edge of observable reality sits. When the metronome splits into two tempos, you are no longer sure what song you are living inside. And humans crave a stable universe for the same reason we crave solid ground, because it allows us to plan, to build, to believe the future is not arbitrary. But the Hubble tension is a reminder that our confidence rests on assumptions that could crumble. If the universe is expanding faster than our early universe story predicts, then our future might be different than we imagine. Dark energy might not be a constant, gentle pressure. It might be something evolving, something capable of changing its mind. And if dark energy can change, the ultimate fate of the cosmos becomes less certain. A universe that accelerates unpredictably is a universe that cannot be trusted to remain as it is. And the cruel irony is that we can't step outside and check. We are trapped inside the experiment. We are creatures made of matter, trying to measure the behavior of matter and space from within matter and space. We have no external vantage point, no cosmic control group, only the sky, only the light, only the numbers we infer. So the disagreement stands. Two rulers, two errors, two answers. And the growing suspicion that neither ruler is broken, that instead the universe is telling us something older and darker. Reality is not finished revealing its rules. And if the rules we thought were stable are not stable, then everything built on them becomes a question. Not just cosmology, everything. In the next part, we'll turn to the first desperate escape route, the hope that this is still just a mistake, an artifact of our instruments, our assumptions, our ladder. We'll walk through the ways scientists have tried to fix the numbers and why the fixes keep failing. Because when every patch you apply only makes the crack more visible, you begin to fear what the crack is leading to. Not a repair, a doorway. The first instinct when the universe contradicts itself is to blame the mirror, not the face. Because new physics is expensive. It demands humility. It demands the admission that our most elegant story might be missing a whole hidden ingredient. And before you rewrite the universe, you interrogate your tools until they confess. So, cosmologists did what any careful species would do. They tried to kill the tension. They tried to make it go away. They looked for a place where human error could hide. a subtle bias, a calibration drift, a systematic mistake so quiet it could survive peer review, survive decades, survive our hunger for a clean number. Because the cosmic distance ladder is powerful, yes, but it is also precarious. It is a chain of trust, and trust is a fragile material. Start with parallax, the geometry rung. It sounds comforting, like it belongs to the safe world of triangles and certainty. But even geometry, in astronomy, is a fight against smallness. Parallax angles are tiny. The shift of a star against the background can be smaller than the thickness of a human hair held at arm's length. Measuring them demands exquisite stability. It demands that your instrument's own subtle distortions be mapped and corrected. Gaia, the great astrometric surveyor, has helped here, giving parallax distances to an ocean of stars with unprecedented precision. But even Gaia is not perfection. Its measurements require careful modeling of spacecraft behavior, detector effects, scanning law geometry, and subtle biases that can imprint themselves into the catalogue. If the foundation rung is tilted by even a whisper, the ladder above it leans. Then come Cepheids. They are beautiful, rhythmic, almost poetic stars that pulse like cosmic hearts. But Cepheids are not identical light bulbs. They live in galaxies with different chemical histories. Some are more metal-rich, some are younger, some sit in crowded regions where other stars bleed into the measurement. Their light can be tinted by dust muffled by interstellar haze, or blended with neighbors into a brightness that is not truly theirs. Crowding is an especially sneaky villain. A Cepheid in a distant galaxy can sit in a dense stellar field. If your telescope cannot cleanly separate it from nearby stars, you accidentally measure the combined light. The Cepheid appears brighter than it is. A brighter candle seems closer. A closer distance means you infer a faster expansion rate. The universe looks like it is running when maybe your eyes are simply overestimating the lamp. So astronomers attacked crowding with sharper vision, better infrared observations, improved point spread, function modeling, and painstaking selection of cleaner Cepheid samples. They shifted to wavelengths, where dust is less cruel. They used telescopes that can resolve tight stellar neighborhoods with less confusion. They compared calibration methods. They tried to tear out the bias by its roots, and still the late universe number stayed high enough to keep the tension alive. Then comes supernovae, the explosive rung. Type Ia supernovae are called standard candles, but that phrase hides a truth. They are not standard by nature. They are standardized by force. We take their messy, violent light curves and correct them, adjusting for how quickly they brighten and fade, for how their color shifts, for how their host galaxies might influence their behavior. We turn chaos into a ruler through calibration, through statistical relationships, through the hope that what remains after correction is universal. But what if the corrections are subtly wrong? What if supernovae evolve across cosmic time, changing their intrinsic properties as the universe ages? What if the environment of the host galaxy, its star formation rate, its metallicity, its dust nudges the explosion in ways our models don't fully capture? What if the standard candle is actually a candle with a flame that depends on where it's burning? Even a small evolution, a slight drift in intrinsic brightness with redshift, could tilt the inferred expansion rate. And this is one of the most unsettling features of the problem. It lives in the regime where tiny biases can create big cosmic consequences. Because you are not measuring an object, you are measuring the space between objects, and that space is enormous. A percent-level systematic error can become a crisis when stretched across the universe. Then there is selection. We like to imagine astronomy as pure observation. But observation is always a kind of filtering. Telescopes find what they can see. Surveys trigger on brightness thresholds. Dusty supernovae may be missed. Faint, fast-fading explosions may slip through the cracks. You build a sample that feels representative, but it is quietly shaped by what your instruments prefer. And when you standardize your candles, you are standardizing a curated subset of reality. A universe observed through selection is a universe already edited. Cosmologists call these effects Malmquist bias, population drift, survey incompleteness, clinical words. But the existential translation is simpler. Even our best maps can be skewed by what we failed to notice. So the community built alternative ladders. If Cepheids are suspect, use different stars. The tip of the red giant branch, old swollen stars that reach a predictable maximum luminosity before igniting helium in their cores, offers a separate standard candle with different systematics. It doesn't rely on pulsation. It doesn't live in the same young crowded regions as Cepheids. It is a different rung built from different physics, and the results became complicated. Some TRGB-based measurements landed lower than the Cepheid ladder, suggesting the tension might soften, but they did not erase it cleanly. They did not snap the late universe into perfect agreement with the early universe. They offered a number that felt like a compromise, but the underlying contradiction refused to die. Then there is gravitational lensing. When a massive galaxy sits between us and a distant quasar, it bends spacetime so strongly that the quasar's light splits into multiple images. Those photons take different paths through curved spacetime, arriving at different times. If the quasar flickers and quasars do, you can measure those time delays. Time delays become distance. Distance becomes expansion. It is a method that feels almost like cosmic sorcery, using the delay of ancient light to measure the universe's scale. But lensing comes with its own monster mass modeling. You must infer the distribution of dark matter in the lensing galaxy, the environment around it, line of sight structures that add subtle extra bending. A wrong assumption about invisible mass can bend your result along with the light. So scientists refine lens models, compare independent teams, test the sensitivity to assumptions. The method is improving. But again, it doesn't produce a clean single number that ends the debate. It becomes another voice in the chorus, sometimes leaning high, sometimes leaving room for doubt, always adding weight to the sense that this is not a trivial error. And then, almost like a whisper from the future, comes the method that bypasses candles entirely. Standard xyrons. Gravitational waves from merging neutron stars carry an intrinsic loudness encoded in their waveform. If you measure the waveform, you can infer the absolute distance to the source without relying on cosmic ladders. If you also identify an electromagnetic counterpart, pinpointing the host galaxy, you can measure its redshift, distance and redshift again, expansion again. But now the ruler is not starlight. It is the trembling of space-time itself. This is the kind of measurement that makes you feel the universe's machinery directly. And it is still young, still limited by small sample sizes, still growing into its power, but it represents a kind of escape from the old uncertainties. A new ladder forged from gravity rather than light. And yet, even here, the universe refuses to be simple. Neutron star mergers are rare and difficult. Counterparts can be faint. Host identifications can be ambiguous. The error bars are wide. The method is not yet sharp enough to end the argument. Not yet. So the tension persists in a strange limbo, not solved, not dismissed, not comfortably ignored. And there is one more possibility, quieter but deeply unsettling, because it suggests the problem might not be in our instruments at all. It might be in our neighborhood. What if the local universe is atypical? What if we live in a region with an unusual density profile, a cosmic valley, a local underdensity, a void-like environment, such that nearby measurements of expansion are biased by local gravitational flows? Galaxies don't just move with expansion, they also fall toward mass, away from emptiness, swayed by the cosmic web's gravitational currents. If we are sitting in an underdense region, local galaxies could appear to recede faster relative to a global average. It is an elegant explanation, and also a haunting one, because it implies something about perspective. The possibility that our measurements are distorted not by human error, but by where we exist inside the cosmic structure. That the universe looks different from different places. That our entire understanding of expansion might be warped by our position in the cosmic landscape, like trying to measure the tide while standing in a whirlpool. Even if this were true, it wouldn't make the universe calmer. It would make it stranger, because it would mean there is no single easy viewpoint from which to measure the cosmos. It would mean we are trapped not only inside the universe, but inside a particular region of it, forced to infer the whole from a biased seat. And suddenly the Hubble tension becomes less like a technical puzzle and more like a philosophical wound. Because if the disagreement is caused by hidden systematics, then we must accept that even our best methods can be deceived by subtle biases we don't fully control. And if the disagreement is caused by our cosmic address, then we must accept that our perspective is not privileged, that the universe does not present itself uniformly to all observers. Either way, the core comfort dies. The comfort that the universe is cleanly measurable. We want the cosmos to be a clock. We want it to tick with one tempo. We want the expansion to be one coherent story from the first light to the last. But the universe is not offering that comfort. The more we interrogate our tools, the more we realize that the tools might not be the problem, or that even if they are the problem is not small enough to be fixed with a simple correction. The tension remains like a shadow that won't detach. And eventually, in every investigation, there comes a moment when you look at the evidence and feel the dread crystallize. What if the measurement is right? What if the ladder isn't crooked? What if the universe really is expanding faster than our early universe story predicts? Because if that's true, then the error isn't in our instruments. The error is in our understanding of reality. And in the next part, we'll step into that darker territory, the possibility that something about the universe's contents, dark energy, gravity, hidden fields, has been mischaracterized. That the cosmos has an ingredient we've never tasted but which has been shaping everything all along. Because if the universe is expanding too fast, and we've measured it correctly, then physics isn't just missing a detail. Physics is missing a mechanism. At some point, the mind stops looking for a smudge on the lens and begins to suspect the sky itself. Because there is a particular kind of fear that only happens when a system you trusted starts behaving like it has secrets. Not the obvious kind, black holes, supernovae, gamma-ray bursts. Those are terrifying, but they are honest. They announce themselves with violence. You can point at them and say there, that is danger. The Hubble tension is different. It is quiet. It hides in a number. It sits inside a decimal place and dares you to ignore it. It doesn't explode. It doesn't glow. It just refuses to agree with itself. And when a refusal persists long enough, it begins to look like a message. Maybe the universe is not contradicting itself. Maybe it's correcting us. Because the standard cosmological story, the one we've been leaning on, makes a set of assumptions so deeply embedded we forget they're assumptions at all. We assume the ingredients are known: ordinary matter, and dark energy. We assume dark energy behaves like a constant, a steady, outward pressure sewn into the fabric of space-time. We assume gravity behaves the same way everywhere at all epochs on all scales. We assume the universe is homogeneous and isotropic. When you zoom out far enough, smooth, fair, statistically uniform. The Hubble tension is the universe asking, what if those assumptions are comforting lies? What if dark energy is not constant? What if gravity is not finished being understood? What if the universe is not as smooth, not as fair, not as symmetrical as we've told ourselves it is? When you say dark energy, it sounds like a thing, a substance, a fluid filling space. But in practice, it's a placeholder for behavior. It's the name we give to the observed acceleration of cosmic expansion. We don't bottle it. We don't catch it in detectors. We infer it because galaxies drift apart in a way that gravity alone cannot explain. In the standard story, dark energy behaves like a cosmological constant. It is the same everywhere and everywhen. It does not clump. It does not evolve. It does not interact. It simply is a baseline pressure of empty space. A clean explanation, a tidy one. And that tidiness is exactly what makes it suspicious when the universe refuses to match our predictions. Because there is another possibility: dark energy has a life. It could have been stronger in the past, weaker now. It could have awakened for a brief era, altering the expansion rate, then faded away like a ghost, leaving fingerprints only on the geometry of the cosmos. It could be a field rolling slowly down an energy landscape we cannot see, changing the expansion history, not with drama but with inevitability. If dark energy evolves, then the universe's timeline is not a straight story. It is a story with a shifting antagonist, an invisible influence that changes its strength over billions of years. That would be terrifying, for the same reason a stable ground turning to soft sand is terrifying. You realize you've been walking on something you assumed was solid. Some cosmologists have entertained the idea of an early surge of dark energy an extra push in the young universe that would change the inferred expansion rate when we project forward from the cosmic microwave background. A temporary ingredient, a short-lived pressure, a cosmic aftertaste. It could reconcile the early universe data with the late universe measurements by changing the evolution between infancy and now. And that idea, while elegant, is deeply unsettling, because it means the universe had an additional phase we did not know about, a hidden epoch where the rules were slightly different, a period where the expansion was nudged by something that is now almost gone, leaving behind only a tension in our numbers. It means reality can run secret subroutines, and if it did once, it can again. Then there is gravity. Gravity is the oldest law we know. It binds your body to Earth, the moon to Earth, Earth to the sun to the galaxy. It sculpts the cosmos into filaments and clusters. It is the force that makes the universe look like something rather than nothing. But gravity is also the law that broke our intuition the hardest. Einstein showed us that gravity is not a pull in the classical sense. It is geometry. Mass and energy tell spacetime how to curve, and spacetime tells matter how to move. A planet falls not because it is grabbed, but because it follows the shape of a warped stage. This was already a kind of existential horror, that down is not a direction but a consequence of curvature. Now imagine that even this is incomplete. Imagine that on the largest scales, the geometry of spacetime is governed by rules we haven't written yet. That general relativity, tested exquisitely in the solar system, confirmed by gravitational waves, validated in countless ways, still fails when the system becomes the size of the observable universe. It's a disturbing thought because it suggests the universe has different regimes of truth, that the laws we treat as universal might be local approximations good within a certain radius of scale and energy, but quietly wrong when applied to everything. And the Hubble tension is exactly the kind of anomaly that could emerge from modified gravity. If gravity behaves slightly differently over cosmic distances, it would change how structure grows, how matter clusters, how expansion evolves. It could change the relationship between the early universe patterns we see in the microwave background and the present universe we measure with supernovae. The universe could be expanding too fast, not because it is being pushed harder, but because our equations for how spacetime responds are missing terms. Missing curvature, missing feedback, missing dimensions. That last word is where the mind begins to tilt, because higher dimensions are not just science fiction decoration. They arise naturally in many attempts to unify physics. And if extra dimensions exist, even if they are hidden or curled up, they could alter gravity's behavior on large scales. They could leak influence into expansion without leaving an obvious trace in everyday life. Reality could be larger than the space we move through, and the expansion could be a shadow of that larger structure. Then there are particles, not the familiar ones, electrons, quarks, photons, the known cast, the ones we can trap and collide and measure in laboratories. Cosmology is haunted by the possibility that the early universe contained additional forms of energy, additional relativistic species, additional neutrino-like particles, additional degrees of freedom that changed the expansion rate when the universe was hot and dense. Even a small extra component in the early universe can alter the way sound waves moved through the plasma, subtly changing the acoustic peaks in the microwave background, subtly shifting the inferred cosmological parameters. And if that is what's happening, then the tension is not merely telling us that our cosmological model needs adjustment. It is telling us there are things in the universe we've never detected directly. Ghost particles, hidden fields, dark sectors interacting only through gravity, living alongside our matter like a parallel ecology we have never seen, shaping the universe's growth like an unseen climate system. The universe might be crowded with invisible life, not biological life, something more alien than biology, forms of existence that don't shine, that don't reflect, that only curve space-time, that only reveal themselves through how the universe expands. This is the cosmic nightmare, an entire population of reality that doesn't announce itself, that doesn't ask to be discovered, that simply influences everything and leaves you to infer its presence from the way galaxies drift apart. And once you accept that possibility, another question rises colder than the others. What if our constants are not constant? We treat the laws of physics like commandments. The speed of light, the strength of forces, the behavior of fields. But we have never proven these are immutable across all time. We assume they are because the assumption makes the universe legible. Without it, the cosmos becomes a shifting dream. Yet, a tension in expansion is exactly the kind of clue that could hint at deeper instability. And instability is where existential dread becomes physical. Because the universe is not only expanding, it is also sitting on foundations we do not fully understand. The Higgs field, for example, gives mass to particles. It is part of the framework that allows matter to be stable chemistry, to exist stars to burn. There are theoretical whispers that the vacuum state of our universe might be metastable, stable for now, but not the lowest possible energy configuration. A false vacuum. If that is true, then reality itself is precarious, balanced in a local valley of an energy landscape. And if it ever tunnels into a lower valley, a true vacuum, it would rewrite the rules of physics instantly at the speed of causality, erasing matter as we know it. No warning, no light to outrun it, no time to understand. The Hubble tension does not prove that nightmare, but it rhymes with it. Because both ideas share a theme, the universe is not obligated to keep the rules the same. The universe is not obligated to be stable. It is not obligated to preserve the conditions that made us possible. We look for comfort in the idea that the cosmos is governed by timeless laws. But perhaps the cosmos is governed by something more like evolution phases, transitions, hidden epochs, changing regimes. A universe that grows, learns, shifts its own parameters. A universe that is not a clock but a process. And processes can turn, they can accelerate. They can enter new phases without asking permission. So, when the early universe and late universe disagree on expansion, it feels like a warning from the cosmic machinery. A small mismatch that may be the first sign of a larger story. A story where dark energy evolves, where gravity changes character, where unseen particles roam, where even the vacuum might not be final. The universe in that story becomes less like a solved equation and more like a living riddle. A riddle with teeth. And in the next part, we'll step even closer to the edge by asking what new physics would actually look like. What kinds of additions could reconcile the numbers? What they would cost us in terms of elegance and certainty? Because every fix to the Hubble tension comes with a price. It makes the universe stranger. And the strangest possibility is this: the universe isn't expanding too fast by accident. It's expanding too fast because we are missing the true shape of reality. When a universe refuses to match its own measurements, you don't just adjust a number, you change a worldview. Because the Hubble tension is not begging for a small correction. It is daring us to propose something that touches the spine of cosmology, the way the universe grows, the way time unfolds, the way space responds to what exists inside it. And the moment you step into new physics, you enter a strange territory where every solution feels like a bargain with the unknown. A fix, yes, but also a cost. You can reconcile the two expansion rates, but only by making the universe stranger than the version we were living in yesterday. And that is where the dread becomes sharper, because it reveals something about our situation. We are not just mapping the cosmos. We are trying to infer the rules of reality from the inside, with a brain that evolved to dodge predators on a savanna. So, what would new physics look like? It often begins with a simple sentence that sounds almost harmless. The standard model of cosmology is missing an ingredient. But ingredient is a deceptive word. It implies something you can sprinkle in like seasoning. In cosmology, an ingredient means an entire new category of existence, fields, particles, forces, behaviors of space-time itself. It means the universe has been running on a set of dynamics we did not know were there. One of the most talked about possibilities is early dark energy. The idea is both elegant and unsettling. In the standard story, dark energy is mostly irrelevant in the early universe because matter and radiation dominate when everything is dense and hot. Dark energy becomes important later, when the universe has expanded and thinned out enough for this subtle pressure to take over and accelerate expansion. But what if dark energy wasn't always subtle? What if, for a brief era, dark energy rose up strong enough to matter in the young universe, then faded away? not a constant, a pulse, a temporary swelling of an invisible field that changed how quickly the early cosmos expanded, changing the sound waves frozen into the microwave background, changing the inferred parameters that we project forward to today. It would be like discovering the universe had an extra heartbeat early on a hidden beat that altered the tempo of its growth. If that were true, then the early universe inference could shift upward, meeting the late universe measurements without accusing the distance ladder of error. A fix. But it comes with a haunting implication: the universe had an extra phase we never knew existed. A brief window where the rules were different, where an unseen field dominated enough to leave fingerprints in the cosmic fossil record, then retreated, leaving no direct trace in the present except a mismatch in our numbers. Reality had a secret episode. And if the universe has secret episodes, it means cosmic history is not just a smooth unfolding, it is punctuated. It can switch regimes. It can change behavior without leaving an obvious scar you can point to with a telescope. It means the universe might be more like a living system than a static machine. Then there's the idea of extra radiation. In the early universe, radiation doesn't just mean light. It means anything that behaves like ultrafast relativistic energy, photons, neutrinos, and any other light species that might exist. If there were additional neutrino-like particles, sterile neutrinos, dark radiation, hidden sector species, then the early universe would expand differently. The timing of recombination would shift. The acoustic peaks in the microwave background would adjust, and the inferred expansion rate today could be nudged. This is one of the most unnerving possibilities, because it implies there may be entire particle families surrounding us that we have never detected. Forms of energy that were abundant when the universe was young, then diluted into near invisibility. A shadow population whose existence is almost gone except for the way it changes the universe's early rhythm. It would mean the universe is not only stranger than we think, it is more crowded, more inhabited. Not by aliens, by physics, by invisible species that shaped the cosmos before stars existed. Then there are solutions that target gravity itself. Modified gravity has always carried a peculiar flavor of dread because it asks you to doubt the most intimate force you know. Gravity is not exotic in your daily life. It's the certainty of weight. It's the reason you don't float away. It's the force that makes the sky feel like it has an up and down. But on cosmic scales, gravity is also the architect of everything. It sculpts galaxies. It binds clusters. It shapes the cosmic web. If gravity is slightly different on enormous scales, then every inference we make about the universe's composition and expansion could be warped. Some modified gravity ideas adjust how gravity behaves at large distances, introducing extra fields that mediate attraction or altering the relationship between curvature and matter. Some invoke screening mechanisms that hide modifications in dense environments, like the solar system, so you wouldn't notice them here, but they reveal themselves across intergalactic space, where density is low and space-time is more fragile. It's almost like gravity wears a mask near us, behaving politely, obeying Einstein's equations, where we can test them best, then changes personality in the deep cosmic dark, where our experiments cannot follow. If that were true, then the universe is not governed by one gravity. It is governed by a gravity that depends on scale. And that idea is terrifying because it suggests the laws of nature are not universally accessible. That physics can behave one way in the environments where we're comfortable and another way where we aren't. The universe would be legible only in pieces, and we are trying to read the whole book from a single chapter. There are also attempts to reconcile the tension by reshaping the matter-content interactions in the dark sector. Dark matter in the standard picture is cold and collisionless. It doesn't interact with light. It doesn't really interact with itself. It simply exists silent, and its gravity does the work. That simplicity is why it fits so neatly into simulations of structure formation. But what if dark matter isn't silent? What if it has its own forces, its own interactions, its own chemistry, except it happens entirely in the dark, invisible to us? If dark matter interacts with dark energy, or if it decays, or if it has pressure-like behavior in the early universe, it could change the expansion history. It could shift the inferred parameters from the microwave background. It could alter the late universe clustering. It could produce exactly the kind of subtle discord we now see. That would mean the universe has a hidden ecosystem that we've been pretending is inert. A dark world with dynamics we cannot observe directly influencing the visible universe, like an unseen ocean current shaping the surface waves. And the unsettling part is that the Hubble tension might be the first time we are forced to admit it. But every one of these proposed fixes has a problem. Not a small problem, an existential one for cosmologists. The universe is an interlocked system. Adjusting one parameter can break others. Add early dark energy, and you must ensure it doesn't ruin the fit to the cosmic microwave background's detailed structure or conflict with measurements of how galaxies cluster. Add dark radiation, and you must not spoil the abundance of light elements forged in the universe's first minutes. Modify gravity, and you must still match gravitational lensing structure, growth, and the behavior of the cosmos across time. The universe is not forgiving. It accepts your new physics only if it fits every other piece of evidence we've collected, like a confession that matches the fingerprints. That's why the tension remains a tension. We have plausible ideas, we have beautiful equations, but the cosmos is a harsh editor. And there is a darker possibility that lurks beneath all of this, quieter and more philosophical, because it doesn't require any specific new particle or field. What if our entire approach is incomplete? What if we're trying to solve a problem that demands a theory we don't yet have? The Hubble tension lives in the space between general relativity and quantum mechanics, two theories that both work brilliantly in their domains and refuse to unify. The early universe is the place where that refusal matters most. It is where space-time is young and dense, where quantum effects might not be small perturbations, but defining features. It is where the concept of smooth space-time may fail. We talk about the Planck length as if it's just a number, an impossibly small scale. But the Planck length is really a warning sign. It's the point where our language about space and time begins to dissolve, where distance and duration might not be continuous but granular, where reality might be foam-like, fluctuating, uncertain. If space-time itself has a quantum structure, then the early universe could imprint subtle signatures that our classical cosmological model cannot capture. The microwave background might be telling us a story we are translating with the wrong alphabet. The inferred expansion rate might be biased not because our instruments are wrong, but because our model of how the universe evolves is missing the deepest layer, the quantum nature of space-time. And if that's true, then the Hubble tension is not a request for a patch. It is a symptom of a missing theory. It is the universe tapping the glass and reminding us that we are not done, that we are still using approximations in the most extreme regime, that our elegant cosmological story might be built on a foundation we haven't actually seen. At this point, the viewer begins to feel the true existential shape of the problem. We are not merely arguing about how fast the universe expands. We are arguing about whether the universe obeys a consistent set of laws across time, whether space-time is smooth or granular, whether dark energy is constant or alive, whether gravity is complete or still wearing a mask, whether the cosmos contains entire sectors of reality that never touch light, and the most haunting thought is that all of these could be true at once. Because the universe is not obligated to choose the simplest option. It has never been obligated to be elegant for our minds. The Hubble tension might be pointing to one missing ingredient, or it might be pointing to a deeper truth that the standard model of cosmology is only a successful approximation, an impressive sketch of a structure far more complex than we can currently resolve. And if the sketch is incomplete, then our predictions about the universe's fate become less certain. The future might not be a smooth slide into heat death. It might be something stranger. Dark energy could evolve into a stronger force, tearing the cosmos apart in a big rip. Or it could decay, changing acceleration into collapse. Or the vacuum itself could be unstable, waiting in silence for a quantum tunneling event that rewrites everything. New physics is not just a new equation, it is a new vulnerability. Because once you accept that the rules can change, you must accept that the universe you live in might not be stable forever, not in the way you assumed, not even in the way physics textbooks promise. And in the next part, we'll tilt fully into the philosophical abyss. If the universe's expansion rate is telling us our model is incomplete, then what does that say about the nature of knowledge itself? Because the most unsettling possibility isn't that physics is wrong. It's that physics is a shadow, an approximation we mistake for truth, while the real universe operates on deeper rules we can barely glimpse. And we are living inside it anyway. There is a moment in every scientific mystery when the mind, exhausted by technical explanations, reaches for a darker kind of logic. Not because it's correct, but because it is emotionally consistent with the feeling of being trapped. The Hubble tension is that kind of mystery. It sits at the intersection of our best instruments and our best theories and still refuses to resolve. It makes the universe feel less like a puzzle and more like a room with a hidden door you can't find. And when you can't find the door, you start to wonder whether the room was designed to keep you in. This is where the thought creeps in. What if reality isn't fundamental? What if the universe is not a self-contained, fully consistent set of laws, but an emergent system, an output generated by deeper rules operating outside our access? The word we use for that in modern language is simulation. It sounds like a meme, a late-night dorm conversation, a philosophical prank wearing the mask of physics. But behind the pop culture gloss is a question older than science itself. Are we seeing reality as it is, or as it is rendered for us? Because the most unsettling thing about the Hubble tension is not just that two numbers disagree, it's that the disagreement appears in the very machinery of measurement. The cosmic ruler itself seems unstable. The scale of the universe, the thing we treat as geometry, as bedrock, turns slippery. And slipperiness is exactly what you expect when you are observing a system with constraints you cannot see. If the universe was simulated, or more broadly, if it were an emergent computation, then it might not be obligated to preserve global consistency in the way a fundamental reality would. It might preserve local consistency where observers live and experiment while tolerating small mismatches at the edges where verification is hardest and consequences are delayed. A world that is rendered does not have to be rendered perfectly everywhere at once. It only has to be coherent enough to be livable. That is a horrifying idea, not because it implies an operator or a creator, but because it implies a limit, a ceiling on what can be known from within, a boundary not of distance, but of epistemology of knowledge itself. The Hubble tension feels like the universe has such a boundary. We try to measure the expansion rate today using nearby cosmic objects. We try to infer it from the earliest light in existence. Both methods are sophisticated. Both are deeply scrutinized, and yet they yield two different answers. If this persists, it suggests either an unknown physical mechanism or a structural limitation in how the universe presents itself to observers. A limitation in the interface. And in a simulated world, interfaces matter more than truth. A simulated system could be designed, or could evolve, so that the laws are stable within a regime and subtly patched across regimes. Not patched maliciously, patched pragmatically, like software that accumulates updates over time, fixes made for one purpose that introduce inconsistencies elsewhere. You can run it for years and never notice until you attempt a measurement that spans too many layers of the architecture. The early universe and late universe might be two layers. The cosmic microwave background would be a fossil record generated under one set of conditions. The present-day universe, measured with candles and ladders and lensing, would be a record under another. If the underlying system changed its internal parameters, or if our theoretical translation between layers is incomplete, we would see exactly what we see now. A disagreement that is small enough to be subtle, but large enough to be real. It would look like physics, with seams, and seams are terrifying because they suggest the world is assembled, not intrinsic. But even if you refuse the word simulation, the same dread survives in a more defensible form. Physics itself hints at limits that resemble rendering constraints. Consider the Planck length, the scale at which our current understanding of space-time collapses into silence. We do not know if space is continuous below that scale. We do not know if time is smooth. We do not know if the universe has a smallest unit of distance like pixels in a cosmic screen. The Planck length is not proof of discreteness. but it is a warning that our smooth equations may be approximations valid only above a certain resolution. And if the universe has a resolution limit, then the universe is in a sense an information system. It processes, it updates, it stores, it evolves. In that picture, cosmic expansion is not merely geometry. It is the evolution of the information structure that defines geometry. And when you hear that the Hubble tension sounds less like a measurement mismatch and more like a synchronization problem, two ways of reading the system's clock that don't align, because the clock is not as simple as we assumed. The dread deepens when you imagine what a civilization far above us might see. We like to picture a Kardashev Type 2 civilization surrounding its star, with machinery harvesting energy on a scale that makes human history look like a flicker. Or a Type 3 civilization spreading across a galaxy, treating stars as infrastructure. Such beings might measure cosmic expansion with exquisite precision using baselines spanning light years, perhaps even millions of light years, turning the universe into a laboratory we can't imagine. And yet even they might face the same contradiction, because no matter how advanced you become, you still measure from within the system. You are still trapped inside the screen. You can refine instruments, you can reduce noise, you can sharpen error bars until the universe feels like it's speaking in crystal clear tones. But if the contradiction is structural, if the system itself has layers, regimes, hidden parameters, then intelligence can only press against the boundary, not escape it. This is why the simulation-like dread is so powerful. It's not about gods or programmers, it's about inescapability. The universe might be the kind of system that can never be fully self-measured from within, an infinite mirror that never reveals the back of its own glass. And if that's true, the Hubble tension becomes one of the first times modern cosmology has brushed against the edge of what can be known. It becomes a great filter of understanding. Not a barrier that kills civilizations with fire, but a barrier that kills certainty with complexity. A stage where scientific progress slows, not because we stop trying, but because the universe stops yielding clean answers. A point where civilizations grow powerful, and still cannot unify their cosmic measurements into one coherent story, because the story is not coherently accessible. Maybe that is why the cosmos seems quiet, not because it is empty, not because life is rare, but because advanced civilizations become trapped in riddles so fundamental they cannot be shouted across the stars, or because they turn inward, chasing the deepest structure of reality and finding only layers and limits. If that sounds bleak, it should, but there is another way this thought could be even worse. In a world that is emergent or simulated, anomalies might not just be accidents, they might be features. They might be the system's way of limiting the inferences observers can make, not through censorship but through complexity, not through deception but through the natural consequence of being inside a system whose full state cannot be observed without occupying more informational capacity than any observer can have. In other words, you cannot know the full universe because knowing it would require being larger than it. So, the universe presents itself in compressible forms, models, constants, averages, smoothness, assumptions. We build equations because equations are compression. We reduce the cosmos to parameters because parameters are the smallest set of numbers that still predict most of what we see. And the Hubble tension might be telling us that our compression has lost something essential, that we have thrown away a bit of the universe's true complexity in exchange for elegance. We keep wanting one number for the expansion rate, one coherent tempo. But what if the universe doesn't have one? What if the expansion rate is not a global constant at all, but a property that depends on scale, environment, cosmic epoch, hidden fields, or the distribution of matter in ways we have not fully captured? What if the universe is more like weather than machinery, patterned, lawful, but not reducible to a single dial? Then the tension isn't a sign that physics is broken. It's a sign that our desire for a single clean answer is the thing that's broken, and that realization is not comforting. It implies the universe may always resist simplification, always remain partly unknowable, not because it is mystical, but because it is too large, too layered, too information-rich to be held in any one mind. or any one theory without loss. Under that view, the Hubble tension becomes a moment of humility, a moment where we look up and feel cosmic awe sharpen into cosmic dread, the awareness that our models might never be the universe itself, only shadows cast by it. Still, there is a final twist, and it's the cruelest one. If the universe is layered, emergent, or informational in its foundations, then its stability is not guaranteed. The vacuum might be metastable. Fields might roll into new states. The constants we compress into neat symbols might be parameters of a deeper system that can drift. And if they can drift, then the universe is not a fixed stage. It is a process that could change, that could transition, that could enter a new phase without warning, like a system reaching a threshold it didn't announce. Which brings us back to the feeling that started all of this. The universe is expanding too fast, and something is wrong. Maybe it's our ladder, maybe it's dark energy, maybe it's gravity, or maybe the deepest truth is that we are living inside a reality whose full architecture is hidden from the inhabitants. An architecture that can leak through in rare contradictions, in tiny mismatches that grow into crises. If so, the Hubble tension is not just a problem to solve. It's a glimpse of the seam, a hint that the universe is not a perfect marble statue, but a constructed thing, whether by physics, by emergence, or by something stranger. And once you've seen a seam, you can't unsee it. In the next part, we'll leave philosophy behind and return to dread. You can quantify what happens if the expansion is truly accelerating in ways we don't understand. What futures open up if the universe's push is evolving? Because if the cosmos is already breaking our models, then the end of the universe might not follow our script either. There is a difference between not understanding the universe and not trusting it. Not understanding is a wound to pride. Not trusting is a wound to safety. Because if the Hubble tension is telling us that something about expansion is off, something about the way the universe evolves is mischaracterized, then the future is not just unknown, it becomes unstable. The kind of unknown where the rules themselves might change mid-sentence. Cosmology has always carried a quiet fatalism. Even in our most optimistic stories, the universe tends toward loneliness. Galaxies drift apart, stars burn out, entropy rises. The cosmos slowly becomes cold and dark. That was the comfortable ending. Comfortable not because it's pleasant, but because it's coherent. Because it feels like a slow fade, a predictable decline. A universe that dies the way a fire dies, gradually, inevitably, with enough time to watch the embers cool. But an expansion rate that refuses to settle, an expansion history that might require evolving dark energy or altered gravity, opens the door to something far less comfortable. A universe that doesn't just fade, a universe that rips. In the standard cosmological model, dark energy behaves like a cosmological constant, a steady pressure that accelerates expansion gently, relentlessly, forever. Under that scenario, the long-term fate is bleak, but smooth galaxies beyond our local group disappear. Beyond the cosmic horizon, star formation dwindles, black holes dominate, and eventually even they evaporate. The end is not a scream, it is silence, heat death, maximum entropy, a universe with no gradients left to fuel complexity. But constant is exactly what is under suspicion. If dark energy is not constant if it evolves, then the fate of the cosmos is not a single line. It becomes a branching tree of endings, each one more unsettling than the last, because each one suggests that cosmic acceleration is not just a background drift, but a dynamic force capable of changing character. The most cinematic nightmare is called the Big Rip. It begins innocently. Expansion accelerates a little faster than we expected. Galaxies recede. Space stretches. We already see this. But if dark energy's equation of state dips into a regime called phantom energy, where its pressure is so negative it grows stronger as the universe expands, then acceleration doesn't just continue, it escalates. In that scenario, the expansion rate increases without bound. Distances don't merely grow, they grow faster and faster. The cosmic horizon shrinks. The universe becomes a machine that tears its own fabric wider with ever-increasing violence. At first, the damage is cosmic scale. Galaxy clusters unbind. The gravitational glue between clusters is overcome by the swelling of space. Whole superclusters become isolated shards drifting into nothing. Then galaxies themselves tear apart. The Milky Way's stars, once bound in a rotating disk, would drift away from one another as if gravity suddenly stopped caring. Then solar systems would unravel. Planets would slip their orbits like beads on a broken string. And in the final moments, the ripping reaches the microscopic. Molecules split, atoms break, nuclei shatter, and finally, space-time itself becomes too violent to maintain any structure at all. Everything becomes a pointless dispersal of fragments. The universe doesn't end by cooling. It ends by shredding. It is hard to describe the existential horror of that without sounding like prophecy, because it isn't prophecy. It's a theoretical fate, a possible branch, but the very existence of that branch is the dread. If dark energy's behavior is uncertain, then the universe's fate is negotiable. It is not written. It can tilt, and we are trying to read the ending while the ink is still moving. Now, perhaps the big rip is too extreme. Perhaps dark energy is evolving in the opposite direction, weakening over time. That opens a different horror, a universe that stops accelerating or even reverses. If dark energy decays, the expansion could slow. It might become dominated again by matter's gravity, and if the balance tips far enough, expansion could halt and reverse into contraction. A big crunch, a universe that collapses back inward, not necessarily into a singularity, not necessarily into a restart, but into an era where the cosmos becomes denser, hotter, more chaotic again. Galaxies collide more frequently. Background radiation grows warmer. The night sky brightens, not with new stars, but with the compressed glow of everything falling together. It's a different kind of end, not tearing but suffocating. And in some speculative models, contraction could lead to a bounce, another beginning, another Big Bang-like event. If so, then the universe is not one story. It is a cycle, a cosmic heartbeat, beautiful and terrifying because it suggests everything you are, every thought, every civilization, every memory, might be one transient ripple in an endless sequence of universes that rise and collapse like waves. There is no grand meaning, only recurrence. Existence becomes a pattern rather than a purpose. But the most disturbing possibility is not the dramatic ends. It is the subtle one-phase transitions. Because if dark energy is a field, not a constant, then it sits on an energy landscape, a kind of potential terrain, and fields can roll. They can get trapped in metastable states. They can tunnel. They can jump. A small shift in a field state could change the laws of physics without warning. Not in a way that tears galaxies apart immediately, but in a way that changes what kinds of structures can exist, what kinds of chemistry is stable, what kinds of stars can burn. In other words, the universe could enter a new phase. And the terrifying part is that phase transitions, once triggered, can propagate, like a crystal forming in a supercooled liquid, like a bubble expanding in a false vacuum. Vacuum decay is the most extreme example. If the vacuum state we inhabit is not the true ground state, then a quantum tunneling event could nucleate a bubble of lower energy vacuum. That bubble would expand at near light speed, rewriting physics as it goes. The constants you rely on, particle masses, force strengths could change. Atoms, as we know them, might be impossible. Chemistry might not exist, and you would never see it coming, because nothing outruns the boundary of such a bubble. There is no warning light, no cosmic siren. Reality would simply end and be replaced by a new set of rules. Again, this is not established fate. But this is exactly the kind of dread that emerges when you realize the universe might not be governed by static parameters. The Hubble tension doesn't prove vacuum decay, but it reminds you that we do not fully understand the fields that underpin reality, dark energy among them. If one fundamental component is behaving unexpectedly, it makes you wonder what else is quietly uncertain, and the universe is full of quiet uncertainties. Now, connect this to the central anxiety. Expansion is not just a fact, it is the stage direction for cosmic history. It determines which structures form, how fast they form, how light travels, how horizons shrink and grow. If the expansion history is wrong, then we are living in a universe whose future we can't confidently extrapolate. We can't say this is how it ends with the old certainty. We can only say, here are branches. And that branching is itself horrifying because it means we might be living in a moment of cosmic instability, an era where the dominant driver of expansion is unknown in its true nature. A time when the universe is young enough for structure and life to exist, but old enough for acceleration to dominate. An era where a wrong assumption about dark energy could mislead us about everything. It also reframes our place in time. Humanity exists at a strange moment. We can still see the cosmic microwave background, still see galaxies far away, still measure the expansion. But the expansion is accelerating, and those galaxies will disappear beyond our horizon. The universe is gradually removing evidence of its own origin. It is erasing its history from view. Imagine a future civilization that rises in a far future Milky Way, long after most galaxies have vanished from sight. They would look up and see a sparse sky. They might not detect the microwave background drowned by local noise or redshifted beyond measurement. They might conclude the universe is static and eternal, a lonely island of stars in an infinite dark. They would be wrong. Not because they are foolish, but because the universe would have hidden its past behind expansion. Cosmic acceleration is a sensor. It locks information beyond horizons. It makes the universe less knowable over time. So even if the Hubble tension is just a dispute about a number, it points to a future where our ability to do cosmology decays. The cosmos is expanding and simultaneously removing the evidence of why. And that is a kind of horror that truth itself has an expiration date. Now the question turns sharper. If dark energy is evolving and the Hubble tension is hinting that it might be, then are we already seeing the first signs of a future branch? A subtle departure from the cosmological constant, a slow drift into new behavior. Is the universe about to do something? Not tomorrow, not next year, not in a way that impacts human lifetimes. But cosmology doesn't measure in lifetimes. It measures in epochs. And the unsettling thought is that we might exist in an epoch where the universe is transitioning, where dark energy is asserting itself in a way we don't fully understand. If so, the Hubble tension is not merely a measurement problem. It is an early warning, a sign that the universe is not settled into its final mode, a reminder that cosmic history is still unfolding under forces we have not named properly. In the next part, we'll connect this uncertainty to another dread that haunts modern science, the silence of the cosmos. The great filter. The question of why we haven't found evidence of other civilizations. Because if the universe's fundamental behavior can surprise us, then perhaps it surprises everyone. Perhaps the Hubble tension is not just a puzzle for astronomers. Perhaps it is part of the reason the universe feels empty. Because advanced civilizations may not be destroyed by asteroids or war. They may be destroyed by reality itself, changing its rules. Or they may be trapped forever, trying to decode the cosmos before the cosmos erases the clues. When you look up at the universe long enough, you begin to feel two emotions that don't belong together. And accusation, because the cosmos is vast beyond comprehension. Trillions of galaxies, each with billions of stars. Planets by the uncountable, the raw material for life scattered everywhere like seeds flung into the dark. Accusation because it should be loud. If life is easy, if intelligence is common, if technology is a natural phase of evolution, then the sky should be full of signatures, radio chatter, engineered megastructures, waste, heat probes, patterns, anything. A universe that old and that large should not feel empty, and yet it does. This is the Fermi paradox. A question disguised as silence. Where is everyone? And the great filter is the terrifying answer shaped like a hypothesis. It says there may be a barrier somewhere between simple chemistry and galaxy-spanning intelligence. A barrier so harsh that almost nothing gets through. Some step in the chain is improbable, or suicidal, or both. We usually imagine the filter as a biological bottleneck, an evolutionary miracle, a runaway self-destruction. But the Hubble tension invites a darker possibility. What if the filter isn't in life? What if the filter is in physics? Because if the universe's expansion is behaving in a way, we do not understand if the fundamental driver of cosmic evolution might be dynamic, unstable, evolving, then every civilization is born inside a system whose rules may not be fully stable. Reality itself becomes the environment, not Earth, not biology. Reality. A civilization can solve engineering. It can solve energy. It can climb the Kardashev ladder, consuming the power output of a planet, then a star, then a galaxy. But can it solve the universe? Can it solve the expansion of space-time itself? Because the Hubble tension is a reminder that even a species capable of measuring the oldest light in existence can still face contradictions at the heart of cosmology. And if those contradictions point to new physics, then any civilization trying to expand into the cosmos faces a terrifying truth. The stage is not fixed. The universe is not just a place you live, it is a process you are embedded in, one that might not be stable. Imagine a Type 2 civilization surrounding its star, an enormous shell or swarm or network of structures capturing most of the star's energy output. It would feel godlike compared to us. It could run computations beyond our imagination, terraform worlds, reshape its solar system into infrastructure. Now imagine that even this civilization is still fundamentally vulnerable to cosmic-scale physics. If dark energy evolves into phantom behavior, the Big Rip will not care how advanced you are. It will unbind your galaxy the same way it unbinds a dust mote. If vacuum decay is real, it will erase a Type 3 civilization as cleanly as it erases a single bacterium because the boundary does not negotiate. It rewrites the rules of matter and chemistry. It doesn't destroy, it replaces. And if the expansion is accelerating in a way that hides information, then the universe itself becomes harder to understand over time, not easier. The cosmic horizon becomes a knowledge horizon. The evidence for the Big Bang slips away. The distant galaxies fade. The microwave background redshifts to wavelengths that become practically unreachable. Truth becomes inaccessible not because anyone is censoring it, but because the universe is expanding it beyond reach. This is the kind of filter that doesn't kill civilizations with violence. It isolates them with ignorance. Even if advanced civilizations exist, they may be trapped in their local gravitational islands, cut off from the rest of the cosmos by expansion, watching the universe's evidence disappear, losing the ability to do true cosmology. Their scientific models could regress not from stupidity, but from missing data. They might become brilliant engineers in a lonely bubble, never realizing how vast the cosmos truly is. And if cosmological knowledge decays over time, then interstellar communication becomes even more unlikely. Not just because distances are huge, but because the universe actively stretches those distances faster. Space is not a neutral medium, it is a moving target. Civilizations might not fail because they don't want to communicate. They might fail because the universe is making communication harder with every passing epoch. Now layer the Hubble tension back into this. If the tension points to new physics, evolving dark energy, dark sector interactions, modified gravity, then the universe is not only expanding, it is governed by components we do not yet understand. That means cosmic engineering may face hazards we can't anticipate. A civilization might build megastructures around stars without knowing whether the expansion rate will shift unexpectedly over billions of years. It might plan for a future it cannot predict accurately because the dominant driver of cosmic evolution is still unknown. It might attempt to spread through the galaxy while the universe's deeper physics quietly changes, altering the stability of stars, the behavior of gravity, the formation of galaxies. And if the universe contains hidden sectors, fields, or particles that interact weakly with ordinary matter, then catastrophic events might occur with little warning. Not daily catastrophes, but existential ones. Phase transitions, shifts in vacuum state, dark sector instabilities, rare events that wipe out complexity, not because complexity is fragile, but because it's built on laws that might not be final. This could be the great filter, not life failing to evolve, but life failing to survive the long-term behavior of the cosmos it's embedded in. And the worst part is that such a filter is invisible until it happens. You would not see a vacuum decay bubble coming. You would not detect a fundamental, constant drifting until its effects accumulate. You would not predict the Big Rip until your theory recognized phantom energy behavior. A civilization could thrive for millions of years, confident in its science, confident in its future, and still be blindsided by physics that turns out to be incomplete. The universe in that story is not hostile, it is indifferent. And indifference is the deepest horror because it offers no antagonist you can negotiate with. There is another twist that makes the silence feel even colder: selection effects in time. We may be early. Not early in the sense of human history, but early in cosmic habitability. The universe took billions of years to enrich itself with heavy elements forged in stars, carbon, oxygen, iron, the building blocks of planets and biology. It also took time for stable planetary systems to settle. Perhaps most civilizations exist in a distant future when more stars have aged, when more planets have formed, when life has had more time. But if that's true, then cosmic acceleration is waiting for them like a trap. The future universe will be more isolated, more empty, more cut off. Civilizations that arise later may find a cosmos with fewer visible galaxies, less accessible information, and a narrower window to understand their own origin. They may not even know the universe is expanding. They may never hear the ancient glow. They may live in a scientifically impoverished sky, which means we might be in a rare moment, an era when the universe still shows its evidence. That thought is both awe and dread. Awe because we are lucky to exist at a time when the cosmos is visible. Dread because it implies that cosmic history includes periods of ignorance that are forced by expansion, not chosen. So the Hubble tension becomes more than a technical debate. It becomes a reminder that the universe can be both intelligible and self-hiding, that it can offer clues and then take them away, that it can allow civilizations to ask the deepest questions and then wall those questions off behind horizons. The Great Filter might be a barrier of comprehension. A civilization might climb the Kardashev ladder and still fail to pierce the deepest layer of cosmology. It might never unify its measurements, never solve the expansion history, never understand dark energy, and therefore never predict the universe's fate. It might live and die inside a story it never fully understood. And if that is common, then the silence makes sense in a bleak way. Civilizations may exist, but they are trapped in cosmic islands, separated by expansion, separated by ignorance, separated by physics. They cannot finish decoding before the universe erases the evidence. Or perhaps they do decode it. Perhaps they discover something even darker. Perhaps they discover that the universe's expansion isn't just an interesting parameter, it is a countdown, a shift toward a phase change, a slow drift toward instability, something that makes long-term survival impossible, no matter how advanced you become. In that case, the silence might not be emptiness, it might be surrender, a cosmos full of minds that realize the same truth too late, that the universe they inhabit is not stable enough to build eternity inside it. We don't know, and that not knowing is the wound. The Hubble tension doesn't answer the Fermi paradox, but it changes the emotional landscape. It makes the silence feel less like a mystery of biology and more like a mystery of physics. It suggests that the most dangerous barrier might not be in life's fragility, but in reality's incompleteness. In the next part, we'll come back down from speculation and return to the edge of what science can currently say with confidence. What the newest surveys and missions are doing to resolve this crisis, and why the answer, when it comes, could reshape our understanding of everything from the universe's age to the fate of cosmic time. Because if the Hubble tension is real, then it is not just a curiosity. It is a crack through which a new universe might be leaking. There is a certain kind of loneliness that only exists at the frontier of understanding. Not the loneliness of being physically alone, but the loneliness of realizing that the universe may be larger than your ability to describe it. That even your best equations, your proudest, cleanest, most elegant ideas might be scaffolding built around something you can't fully see. This is where cosmologists live now. They are not looking at the stars the way poets do. They are looking at the stars the way detectives look at fingerprints. Every photon is evidence. Every spectrum is testimony. Every faint distortion in the shape of a galaxy is a clue about the invisible gravity that bent its light. And somewhere in those clues is the answer to a question that should have been settled: how fast is the universe expanding? Because the Hubble tension has done something profound to cosmology. It has turned the entire sky into a courtroom. It has forced every dataset to take the stand. It has made the universe feel less like a solved object and more like a living suspect, cooperative, in some ways evasive in others. So the scientific world responds the only way it knows how, by building eyes. New eyes, sharper eyes, wider eyes. James Webb stares into the infrared, peeling away dust and reaching farther into cosmic time, watching early galaxies as they form, trying to understand whether our assumptions about stellar populations and distances are as stable as we claim. It doesn't just see deeper, it sees differently, slicing through the cosmic fog where older telescopes saw blur. It is not a single answer machine, it is a clarifier, a tool that reduces the places where bias can hide. Euclid scans vast regions of sky, looking for subtle distortions, weak gravitational lensing, where the shapes of galaxies are stretched by the gravity of dark matter between us and them. It is mapping the invisible scaffolding of the universe, as if tracing the outline of a monster by the way it bends the air around it, because how matter clusters over time is tied to how the universe expands. The geometry and the growth are not separate stories. They are braided. DESI listens to the universe's large-scale rhythm by measuring the positions and redshifts of millions of galaxies. It is hunting the imprint of ancient sound waves, the baryon acoustic oscillations frozen into the distribution of matter, like a cosmic fossil. Those ripples act like a ruler, not built from stars that might evolve, but from the universe's own primordial heartbeat. A standard ruler stretched across space, carved into the cosmic web. And then there is the looming promise of the Vera Rubin Observatory, designed to watch the sky in time-lapse, catching supernovae as they bloom and fade by the thousands, building a statistical empire of explosions. Because sometimes, the way you defeat uncertainty isn't with a single perfect measurement, it's with overwhelming repetition, a flood of data so vast that random errors drown, leaving only the systematic demons behind. And beyond all of this, more instruments wait, space telescopes, built to measure weak lensing, to map galaxies, to track the growth of structure with unprecedented clarity. A new generation of cosmology that treats the universe less like a distant backdrop and more like a system whose parameters can be extracted if only you measure enough of it. But here is where the dread sharpens. More data doesn't always mean more peace. More data can mean more detail, and more detail can reveal deeper contradictions. There is a seductive idea that science is a straight climb toward truth, that if you just build a better telescope, the universe will finally confess. But the universe does not confess like a human. It does not have a single statement hidden in its pocket. It has layers, regimes, scales that behave differently, clues that change meaning depending on what you assume about the hidden components. Because cosmology is not just about looking, it's about translating. When you measure a redshift, you're reading the stretching of space. But to turn that into a distance, you must choose a model of how the universe has expanded across time. When you measure the cosmic microwave background, you're seeing the earliest light, but to infer today's expansion rate, you must evolve that early picture forward through billions of years of physics. When you map galaxies, you're seeing structure, but to convert structure into constraints, you must assume how dark matter behaves, how baryons behave, how gravity behaves. Every measurement is a conversation with a model, and when the model is incomplete, the conversation becomes haunted. This is the edge of knowledge, the point where a single discrepancy can be interpreted in more than one way, and where every interpretation carries existential consequences. If the tension is born from hidden systematics in the distance ladder, then the universe isn't broken, our methods are. But that is not a comforting conclusion. It implies the cosmos is harder to measure than we believed. It implies that even when we think we are holding a standard candle, the flame might be flickering in ways we can't fully correct. And if the tension points to new physics, then the implications are even larger. Because new physics is not just an added detail. It is a rewrite of the framework that connects the early universe to the late universe. It is a shift in the story of how reality itself evolves. This is why the Hubble tension has the emotional weight of a crisis. It is not that cosmologists are afraid of being wrong. Scientists live with wrongness as a daily companion. It is that being wrong here means being wrong about the cosmic foundation. It means that dark energy might not be constant. It means that gravity might not be complete. It means that there may be a hidden sector of reality fields, particles, interactions that only reveal themselves through the way the universe expands. And expansion is not a minor feature. Expansion is the universe's clock. So now, every new survey is not just a measurement, it is a test of reality's consistency. Weak lensing asks, does structure grow the way our gravity predicts in an accelerating universe? BAO asks, is the standard ruler consistent across redshift, or is the distance-redshift relation subtly warped? Supernova samples ask, are our candles truly standard across environments, or are we imposing a correction that hides evolution? Gravitational waves ask, can space-time itself become our ruler, bypassing light's uncertainties? And each probe has its own ghosts, its own systematics, its own assumptions. So cosmology becomes a strange ritual: measure the same truth in a dozen ways and see if the answers converge, not because you distrust the universe, but because you distrust yourself. And yet beneath this careful scientific humility there is a more haunting question. A question that surfaces only when you stare at the enormity of the universe and remember what we are. Tiny organisms on a thin membrane of rock, reading cosmic history from light that is barely there. Can we actually solve it? Not in the sense of giving up, not in the sense of surrender, but in the deeper sense, does the universe allow itself to be fully reconstructed from within? Because there is a fundamental asymmetry we cannot escape. We see only what light can reach us. We see only what lies within our horizon. We see only a single slice of cosmic time, our era, trying to infer the entire timeline from it. The universe could have features that are globally true but locally invisible, structures larger than our observable volume, phases that occurred before the universe became transparent, mechanisms that operate in regimes we can't probe directly, a dark sector that barely touches our matter, a geometry that looks smooth at our resolution but is granular at the Planck length. In that case, the Hubble tension may be a symptom of an even deeper limitation, that the universe is not fully self-disclosing, that some truths are not accessible from the inside without loss. And if that is true, then cosmologists are not just trying to solve a puzzle, they are trying to overcome a boundary condition of existence. Still, there is awe here too, because even the fact that we can ask this question is absurd. We are made of atoms forged in stars, and those atoms have arranged themselves into minds capable of measuring the afterglow of the Big Bang. We have built machines that can detect the stretching of space-time by passing gravitational waves. We have built telescopes that can see galaxies so distant their light left when the universe was still young. That alone should fill you with cosmic awe, that the universe can produce observers who can partially understand it. But dread returns, because partial understanding is a painful place to live. It is like hearing the first notes of a song and realizing you may never hear the ending. Like finding a door in a dark hallway and realizing it opens into another hallway, not an exit. If the Hubble tension resolves, if future measurements converge on one number, then we will breathe briefly. We will patch our story. We will declare the crisis over. But if it does not resolve, if the tension remains as instruments sharpen, then we will have to accept something stranger, that the universe has an ingredient we missed, a mechanism we have not named, a rule we have not written. And that will be both terrifying and beautiful. Terrifying because it means reality is deeper than our current understanding, and therefore more unstable than our current predictions. Beautiful because it means the cosmos still contains mysteries worthy of its size, that we haven't reached the end of the map, that there are still undiscovered continents in physics. This is where we stand now, at the edge of knowledge, listening to the universe argue with itself through our instruments. And the argument is not just academic, it is about what kind of universe we live in. A universe that is consistent and calm beneath its vastness, or a universe that is evolving its own rules while we watch. In the next part, we'll ask the simplest question with the most frightening implications. What happens if we never reconcile the numbers? What if the tension becomes permanent? What if the universe refuses to give us one coherent expansion rate? because then we are not just missing a value, we are missing the shape of reality. There is a kind of terror that doesn't come from catastrophe. It comes from permanence, from the possibility that a question can remain open, not because we are lazy, not because we lack tools, but because the universe itself refuses to become fully legible. Because the deeper you look, the more the cosmos behaves like something that can be measured in fragments but never held whole. That is the nightmare hidden inside the Hubble tension. Not that we're wrong, not even that physics needs an update, but that the universe might not allow a final answer in the way we crave. Imagine it decades pass, surveys expand, telescopes sharpen, error bars shrink like closing jaws. The cosmic distance ladder is rebuilt with better calibration. Gravitational waves become routine. Millions of supernovae are catalogued. Weak lensing maps dark matter with frightening clarity. Every major systematic is hunted, modeled, corrected, and still the two expansion rates refuse to converge. Not because the instruments are failing, but because the universe itself is telling a truth that doesn't fit into a single number. At that point, the Hubble tension becomes something else entirely. It stops being a tension and becomes a new feature of reality, like the speed of light or the existence of quantum uncertainty. A permanent scar in our attempt to compress the cosmos into clean parameters. And what would that mean? It would mean the Hubble constant is not constant in the way we wanted it to be. It would mean the universe might not have one global expansion rate that can be measured consistently from all directions and all epochs. It might have an expansion history that depends on environment, on scale, on time, on hidden fields and sectors, on the local density of matter or on the geometry of spacetime in ways that refuse simple summarization. In other words, the universe might be too complex to be reduced to the kind of model we prefer. Humans love compression. We do it with language, we do it with numbers, we do it with laws. We take a storm of data and reduce it to a few equations that fit on a chalkboard. That is how we build civilization. That is how we build technology. That is how we survive. But the universe might not be compressible to our satisfaction, and that would be a deep kind of defeat, not a defeat of effort, but a defeat of elegance. It would mean that our standard model of cosmology, as successful as it has been, might be the cosmological equivalent of Newtonian gravity, an approximation that works astonishingly well in many regimes, but fails in subtle ways when pushed to extremes. And that's not just an academic problem, because if the expansion history remains uncertain, then everything we build on it remains uncertain too. The age of the universe becomes less precise. The inferred sizes of cosmic distances become less precise. The timeline of galaxy formation becomes less certain. The fate of the universe becomes harder to predict. We stop being able to say with a straight face that we know how old everything is or how the cosmos ends. We can give ranges, possibilities, branches, but the clean story dissolves, and this is where existential dread becomes practical. Because human meaning is often built on the idea that the universe is understandable, that the laws are stable, that progress in knowledge is a straight ascent toward clarity. If the Hubble tension becomes permanent, it suggests a different kind of universe, one where knowledge has ceilings, where some questions remain perpetually at the edge, because the evidence is always filtered through horizons and assumptions, and the limitations of being inside the system. A universe where science does not end in certainty but in asymptotic frustration. You can get closer and closer to truth but never reach it fully. Now imagine a civilization 1,000 times more advanced than us. A Kardashev civilization that harvests a star, that builds structures the size of planets, that bends asteroids into art. They might think of themselves as masters of their environment. They might measure cosmic expansion with exquisite precision, treating the universe like an engineering problem. But if the Hubble tension reflects a fundamental limitation, if expansion is not a single coherent parameter, then even they may be trapped in uncertainty. Even they may never unify the early and late measurements into one clean number. They may have more data, but the same essential problem, the universe, is not obligated to be simple. In that scenario, the great filter we spoke about becomes a filter of comprehension, not a sudden death event, but a boundary where advanced civilizations stop being able to construct a single unified cosmology. They may become technologically powerful and still cosmologically blind, living in a universe whose deepest structure is partly inaccessible. And there is another layer of horror: information loss. The accelerating universe is already erasing evidence. Distant galaxies recede beyond our horizon. The cosmic microwave background becomes ever more stretched, ever fainter, ever harder to detect. The universe doesn't just hide truths behind distance, it hides truths behind time. If the tension remains unresolved long enough, the possibility emerges that the window to solve it could close, not because the universe changes, but because the evidence drifts out of reach. This is a particularly cruel concept: that truth has a deadline, that the universe's expansion is not just a physical process, but an epistemic one, an engine that slowly makes the cosmos less knowable. In that sense, the Hubble tension is not simply an argument about the expansion rate. It is part of a larger story that the universe may become progressively harder to understand as it ages, because it isolates observers and erases distant reference points. We are living in an era where the cosmos still shows its scars, but the scars will fade, and if we fail to read them in time, future civilizations might never know what we once knew. They may inherit a sky that offers fewer clues. They may never infer the Big Bang correctly. They may never detect dark energy. They may never see enough galaxies to realize the universe is expanding at all. They might build their science around a false cosmology, not from stupidity but from missing evidence. That is a kind of cosmic tragedy intelligence rising in a universe that has already hidden its own origin. So what happens if we never solve it? We are forced to live with a universe that has an unresolved contradiction at its center, a universe whose expansion rate cannot be pinned down with a single voice. A universe where our best models remain provisional, not because science is weak, but because reality is deep. And there is a strange psychological cost to living in such a universe. Because humans don't just want knowledge, we want closure. We want a clean ending to our questions. We want the comfort of thinking the universe is an equation with a final solution. But perhaps the universe is not a final solution. Perhaps it is a system that generates questions faster than answers. If that is true, then the Hubble tension is not a failure of science. It is a revelation about the nature of knowledge, that understanding may always be partial, always improving, always asymptotic. That the best we can do is build models, that work models, that predict, that guide, that approximate, even if the deepest layer remains hidden. This is not despair. It is a kind of cosmic humility. But humility is painful when you are a species that built its identity on understanding. So the viewer is left with a haunting thought. If we never solve the Hubble tension, then our picture of the universe will forever contain a crack, a place where the laws do not close, a reminder that reality is not obligated to be consistent with our expectations. And once that possibility exists, it changes the way you look at every other cosmic claim: the age of the universe, the shape of dark energy, the future of acceleration, the stability of the vacuum, even the existence of a single coherent cosmological model. All of it becomes less like scripture and more like hypothesis. And in a universe that is always a hypothesis, the dread never fully leaves because your foundations are never fully solid. Yet there is awe in that too, because a universe that cannot be fully compressed is a universe that remains vast, not only in size but in meaning. It means the cosmos still has rooms we haven't entered. It means our curiosity is not obsolete. It means we are not at the end of discovery, even if the price of that discovery is the realization that some truths might always remain just beyond our grasp. In the final part, we'll end where we began, with the sky above expanding, carrying galaxies away, and with the chilling question that sits beneath the Hubble tension like a heartbeat. If our equations are wrong, what else about reality is wrong? And what does it mean to live inside a universe that keeps its deepest rules half hidden? Look up tonight if you can. Find a patch of sky away from city light. Let your eyes adjust. Let the darkness thicken. You will see stars, first nearby sparks. Then, if you're lucky, a pale smear of the Milky Way. A soft band of light that isn't a cloud but a billion suns seen edge on. and then the feeling will arrive that you are inside something unimaginably large. It's not just that the universe is big, it's that it is big in a way your brain was never designed to hold. You can say billions of light years, like you're saying a number, but you cannot truly feel it. Your mind tries to picture distance and fails. It retreats to metaphor, ocean, desert, abyss. But the abyss is closer to the truth than we like to admit. Because the most haunting thing about cosmology isn't the violence of black holes or the coldness of the void. It's the fact that the universe is not finished explaining itself. The Hubble tension is a small phrase for a gigantic unease. It sounds like a technical detail, something only academics should care about, but it is actually a crack in the foundation of the cosmic story, a disagreement between the universe's first light and the universe's present motion, a contradiction in the metronome that sets the tempo of everything. And once you realize that, you begin to understand why it feels existential, because the expansion rate isn't just a measurement, it's the scale of reality. It is what tells you how far away things are, how long ago they happened, how old the universe is, how much time galaxies had to form, how fast the cosmos is erasing its own evidence behind the horizon. It is the invisible flow of the river you are standing in, and that river is moving faster than it should, or at least faster than our story predicts. We have tried to make the tension go away. We have sharpened our instruments. We have rebuilt the ladder. We have cross-checked the candles. We have turned quasars into timepieces and gravity into a ruler. We have stared into the microwave afterglow of the Big Bang and listened to the universe's infant heartbeat, and still the numbers do not reconcile easily. So you are left with three possibilities, and none of them are comforting. Maybe we are measuring the universe wrong. This sounds safe, but it isn't. It means our methods are vulnerable to biases so subtle they survive our best scrutiny. It means we can build exquisite machines and still be seduced by hidden errors. It means the universe is harder to measure than we believed and therefore harder to know. Maybe the standard model is missing something. A new field, a new particle, a new interaction, a dark sector that behaves like an invisible ecology, an early pulse of dark energy, a gravity that changes character across scale. Something that alters the bridge between the early universe and the present, making our predictions wrong, not because our math is bad, but because our story is incomplete. This is exhilarating and terrifying, because missing physics means the universe has hidden mechanisms. It means reality is deeper than our current laws. It means the cosmos has compartments we haven't opened. And compartments imply surprises. Or maybe the universe is not the kind of thing that yields a final clean answer from within. Maybe the expansion rate is not a single global dial. Maybe our insistence on one number is a human craving for simplicity imposed on a system that is not obligated to be simple. Maybe the universe is lawful but not compressible. Maybe it is coherent but layered. Maybe truth exists but cannot be held entirely by observers trapped inside the system. That is the bleakest possibility because it implies a limit not of intelligence but of perspective. You cannot step outside the universe to measure it. You cannot compare it to another universe in a controlled way. You only have one sky, one era, one vantage point and light that has been stretched and distorted by the very expansion you are trying to understand. So the Hubble tension becomes a mirror held up to humanity. It reveals something about our relationship to knowledge. We are a species that built its meaning around understanding, around the belief that if we ask enough questions and build enough tools, the universe will eventually surrender its secrets. But perhaps the universe does not surrender. Perhaps it only offers glimpses. And glimpses are both gift and curse. A gift because even a glimpse can change everything. A curse because a glimpse proves there is more and you may never see it all. Still, there is a strange kind of hope hidden in this crisis, because a universe with unresolved contradictions is a universe that still contains discovery. A universe that can surprise us is a universe that is still alive intellectually. It means we are not at the end of physics. It means the cosmos is not a closed book. It means the great mysteries, dark energy, the nature of space-time, the possibility of vacuum instability, the reason the universe has the laws it has are not relics of the past but active questions. And perhaps that is the true cosmic condition to exist inside a reality that is bigger than any one story. Think of the Planck length again, not as a number, but as a warning, a boundary where our language about space and time begins to fail, a place where continuity might dissolve. If the smallest scales are uncertain, then the largest scales being uncertain is almost poetic in a cruel way. The universe is opaque at both ends, too small, too large, leaving us in a middle zone where we can build models that work but never feel entirely finished. We are not gods reading the universe like a blueprint. We are inside the blueprint trying to infer the architect's intentions from the shape of the walls. And the walls are expanding, faster than expected. Which brings us back to the simplest question of all, the one that hums beneath every dataset and every equation like a low cosmic note. If our equations are wrong, what else about reality is wrong? Are we wrong about dark energy being constant? Are we wrong about gravity being complete? Are we wrong about the stability of the vacuum? Are we wrong about how the universe began? Are we wrong about its fate? Are we wrong about our place in time? About whether we live in a rare era where the cosmos is still visible before expansion erases its evidence? And perhaps the most haunting question, if we are wrong about the biggest thing we can measure, what does that say about the smaller things we believe we understand? Not to collapse into cynicism, but to remember what science truly is, not certainty, but a disciplined way of being wrong until you are less wrong. The Hubble tension is a reminder that knowledge is not a fortress, it is a shoreline, and the ocean keeps moving. So the sky above becomes stranger, not less beautiful, more beautiful, because beauty in science is not only in answers. Beauty is in the questions that survive, in the mysteries that refuse to die, in the realization that reality is not an object we possess, but a horizon we approach. And as the universe expands silently, relentlessly carrying galaxies beyond our reach, erasing its own history from view, accelerating into a future we cannot yet name, we are left with a final haunting thought. Maybe the universe is not a story that ends. Maybe it is a question, and we are a brief moment inside it, conscious enough to notice the contradiction, small enough to be terrified by it, and lucky enough just barely to ask, what is the universe doing? And why does it feel like something is wrong?